Look up at the night sky on a clear evening, and what do you see? Countless stars, perhaps a planet or two, the familiar moon. It all seems so peaceful and orderly, almost like clockwork. But what if I told you that our solar system, that seemingly well-behaved cosmic neighborhood we all learned about in school, is actually home to secrets so profound and mysteries so baffling that even the brightest minds on Earth are still scratching their heads? Think about that for a moment. We've sent probes to every planet, landed on Mars, flown by Pluto, and yet there are questions right here in our own celestial backyard that remain utterly unresolved. What secrets lie hidden just beyond our reach, silently orbiting our sun, waiting for someone, maybe even you watching this, to finally uncover the truth? This video is an invitation to step into that unknown, to explore the edges of our understanding and wander through the cosmic puzzles that continue to defy explanation. We're going to journey together through 30 of the most captivating, head-scratching mysteries our solar system has to offer. From bizarre weather patterns on gas giants that shouldn't exist to strange, unexplained objects drifting in the darkness, each of these enigmas tells a story, not just about planets and moons, but about us. About our endless curiosity, our drive to explore, and that deep human need to look up at the stars and wonder what's really out there. This isn't just a list of facts, it's a voyage into the heart of discovery itself, where every unanswered question is an opportunity to marvel at just how much we have yet to learn. So get comfortable, open your mind, and let's embark on this adventure side by side. Whether you're a lifelong space enthusiast or someone who's just curious about the universe, there's something here for you. A chance to reconnect with that childlike wonder we all once felt, staring up at the sky and dreaming of the impossible. By the time we're done, you'll see our solar system in a whole new light, not as a static diagram in a textbook, but as a dynamic, mysterious, and breathtakingly strange place that's still full of surprises. Ready to explore? Let's begin. Our journey into the solar system's greatest puzzles begins not in the cold, outer darkness, but closer to home, shrouded in the thick, crushing atmosphere of our so-called sister planet. Venus is a world of extremes, a hellscape with surface temperatures hot enough to melt lead and air pressure that would feel like being a kilometer under the ocean. But high above that inferno, something truly bizarre is spinning. At the planet's south pole, there is a storm unlike any other we see in the solar system, a massive, swirling double vortex. Picture this, if you will, not one but two distinct, connected eyes of a hurricane, endlessly churning in a permanent and perfectly balanced dance. This isn't a temporary weather event. It's a permanent feature of the Venusian atmosphere, a giant whirlpool of toxic gases locked in place over the pole. What makes this so mysterious? For one, we simply don't understand the engine that keeps it running. Our own hurricanes on Earth are powered by warm ocean water and eventually dissipate when they move over land or cooler waters. Venus has no oceans. There's no obvious source of energy to drive such a persistent and perfectly structured storm. The vortex was first glimpsed by Pioneer Venus in the 1970s, but it was the European Space Agency's Venus Express orbiter in 2006 that gave us our first detailed, long-term look, revealing its complex and dynamic nature. The two centers of the vortex can change shape dramatically, sometimes appearing like a giant bow tie, other times like an elongated letter S, and they can even rotate around each other independently. It's a chaotic system that somehow maintains its overall stability, defying our basic models of atmospheric fluid dynamics. Scientists have proposed various theories. Some suggest it's a product of the planet's superrotation, where the entire Venusian atmosphere whips around the planet much faster than the solid globe itself rotates. Others point to complex wave patterns and temperature differences between the planet's equator and its poles. But no single computer model has yet been able to fully replicate the vortex's strange and stable duality. It stands as a stark reminder that even on a planet we've been studying for decades, fundamental processes can still elude us. The Venusian vortex is more than just a curious cloud formation. It's a window into the complex and poorly understood forces that shape planetary atmospheres, a swirling enigma that challenges our very definition of what weather can be. And yet, for all its fiery drama, Venus is not the only inner planet holding onto a deep secret. If we journey sunward to the scorched and airless world of Mercury, we find a mystery not of atmosphere but of anatomy, a planet that is quite literally shrinking before our eyes. Conventional wisdom told us that small planets, lacking the internal heat of their larger cousins, should cool down rapidly, solidify completely, and become geologically dead worlds. Mercury, the smallest of all, should have been the first to retire from geological activity, a static fossil from the solar system's violent birth. But the data from NASA, a messenger mission, painted a radically different and far more dynamic picture. Messenger detailed orbital survey revealed a global network of colossal cliffs snaking across the Mercurian surface. These are not like the mountains on Earth, pushed upward by colliding tectonic plates. These features, called lobate scarps, are essentially giant wrinkles. They form as the planet's interior cools and contracts, causing the still cooling core to solidify and shrink. With the inside getting smaller, the planet's brittle outer crust has no choice but to crumple and fracture, thrusting sections of itself upward and over others to accommodate the reduction in volume. It's the cosmic equivalent of a raisin drying out and shriveling up, but on a planetary scale. The sheer scale of this process is what truly astonishes. One of the most dramatic features discovered is a vast trough system known as the Great Valley in the planet's southern hemisphere. This isn't a valley carved by water or wind, it's a tectonic artifact. It stretches over 1,000 kilometers long, 100 kilometers wide, and plunges 3 kilometers deep. This valley was formed as the crust was pulled apart by the global contraction, causing a section of the surface to literally drop down between two fault lines. Its existence is a direct and dramatic testament to the incredible forces still at work within this small world. Here's the profound mystery that has planetary scientists rethinking their textbooks. Mercury is much smaller than Earth, and it should have lost its internal heat billions of years ago. The contraction itself isn't the surprise, it's the fact that it seems to be ongoing. The scarps are remarkably fresh-looking, largely unblemished by the cratering that marks ancient surfaces. This suggests that this global shrinkage isn't some ancient, concluded event. It is a process that is likely still happening today. Mercury, against all odds, remains a geologically active world. This forces us to reconsider what keeps a planet's engine running. What internal heat source, what slow radioactive decay in its core, is potent enough to drive this activity for over 4.5 billion years on such a small body? The answer doesn't just rewrite the story of Mercury. It challenges our fundamental assumptions about how all rocky planets, including those orbiting distant stars, live and die. This tiny, shrinking world is proving to be a giant in revealing the dynamic and ever-changing nature of planetary evolution. But if Mercury and Venus challenge our understanding of planetary mechanics, the next mystery strikes at the very heart of our search for life beyond Earth. For centuries, Mars has been the focal point of our extraterrestrial dreams, a world that feels almost familiar with its dusty red plains and polar ice caps. And in recent years, our robotic explorers on the surface have been sniffing the air, making a detection so tantalizing and so perplexing that it has become one of the most debated topics in planetary science. They have found methane. Now on Earth, the vast majority of atmospheric methane is produced by living organisms, from microbes to cows. It's a gas that, in the right context, can be a powerful signature of biology, a biological beacon. So when NASA Curiosity rover began detecting sporadic, unpredictable puffs of this gas wafting through the Martian air, the scientific community was set abuzz. The mystery isn't just that methane is there, it's how it behaves. This isn't a constant, steady background level of gas. Curiosity's sophisticated onboard laboratory, the sample analysis at Mars Instrument, has recorded dramatic spikes where the methane concentration suddenly surges to around 10 times the baseline level, only to vanish again just as quickly. Even more intriguing is a potential seasonal cycle, with background levels seeming to rise and fall with the Martian seasons, peaking in the northern hemisphere's late summer. This behavior is bizarre because methane on Mars should be stable. The Martian atmosphere is constantly bombarded by ultraviolet radiation from the sun, which should break methane molecules apart in a matter of centuries. For us to be detecting it at all, and especially in these sudden, violent bursts, there must be an active, ongoing source replenishing it, and something must be destroying it far faster than our models predict. This leads us to the multi-billion-dollar question: what is producing it? The explanations fall into two captivating and utterly opposed categories. The first and most thrilling is biology. Could subterranean colonies of Martian microbes, known as methanogens, be alive right now beneath the frozen surface, metabolizing nutrients and producing methane as a waste product, just as their terrestrial cousins do? It's a breathtaking possibility that these fleeting whiffs of gas could be the first whisper of a second genesis of life, happening right next door. The second category is geology. Methane can also be produced by abiotic processes, specifically through reactions between water, carbon dioxide, and certain types of rock like olivine in a process called serpentinization. This would require liquid water to be interacting with rock deep underground, which is itself a fascinating prospect, pointing to potentially habitable subsurface aquifers even if no life is present. There's even a possibility that the methane is ancient, trapped in ice like clathrate compounds underground for eons, and only now being occasionally and unpredictably released by geological shifts or seasonal thaws. The maddening part is that we still lack the definitive evidence to choose between these stories. Follow-up observations by the Trace Gas Orbiter, a European spacecraft designed specifically to sniff out atmospheric gases from orbit, have often found nothing, no methane at all, even when Curiosity is measuring a spike right below it. This discrepancy only deepens the puzzle, suggesting the methane is not only sporadic in time but also incredibly localized, dissipating almost the instant it reaches the open air. It's as if Mars is teasing us, offering a clue and then snatching it away before we can determine its origin. This methane mystery is far more than a chemical curiosity. It is a scientific detective story of the highest order, a cosmic whodunit where the suspect could be a microbe or a rock, and the implications of either answer will fundamentally reshape our place in the universe. This brings us to a mystery not of gas but of force, a puzzle buried deep within our closest celestial companion. We look up at the moon today and see a silent, airless, geologically dead world. It's a museum of impact craters, a fossilized record of the solar system's violent youth. But the rocks brought back by the Apollo astronauts tell a far more dynamic story. Locked within their ancient crystals is the astonishing evidence that the moon once possessed a magnetic field, and not just a weak one. For nearly 1 billion years, the early moon generated a field likely as strong as Earth's is today. This presents a monumental head-scratcher for planetary scientists. How could such a small world, which should have cooled and solidified rapidly, power a planetary-scale dynamo for so long? A magnetic field is a planet's invisible shield generated by what's known as a dynamo effect. This requires a churning, convecting, liquid metal core, a great spinning engine deep inside a world. Earth has a powerful dynamo thanks to its large, still molten iron core, which is constantly stirred by the heat released from the radioactive decay of elements and the slow solidification of the inner core. The moon, with just a fraction of Earth's mass, presents a completely different thermal reality. Its small size means it should have lost its internal heat incredibly fast, its core solidifying and any magnetic dynamo sputtering out within a few 100 million years of its formation. The Apollo samples prove this simple story is wrong. The lunar dynamo wasn't a brief flicker, it was a long-lasting blaze that persisted for an astonishingly long time. So what was the power source? What colossal engine could have kept the moon's core churning for so long? Scientists have proposed several compelling and sometimes wild theories. One leading idea points to a phenomenon called precession. Imagine a spinning top just as it starts to wobble before falling over. The early moon orbited much closer to Earth, and our planet's gravitational pull would have exerted a tremendous torque on the moon's solid mantle. This force could have caused the mantle to wobble or precess relative to the liquid core inside it. This differential motion, the solid shell sloshing against the liquid center, could have acted like a giant spoon, stirring the molten iron core with enough vigor to generate a magnetic dynamo. It's an elegant solution that uses the moon's unique orbital relationship with Earth as its battery. Another theory suggests the dynamo was fueled by giant impacts that rocked the young moon. The final stages of planetary formation were a chaotic bombardment, and a massive strike could have delivered a huge surge of energy, reheating the core and restarting the convective engine. There's even a hypothesis that points to the slow, gradual crystallization of a mineral layer at the boundary between the core and the mantle. As this blanket of minerals solidified, it would have released latent heat and buoyant material, effectively powering a slow, steady convection in the core for eons. Each theory has its merits, but each also faces significant challenges. Precession, for instance, would have been most powerful when the moon was closest to Earth, yet the magnetic field evidence suggests it remained strong even as the moon drifted farther away. Impact heating would be violent but sporadic, making it difficult to explain the field's long-term stability. The mystery of the moon's magnetic field forces us to reconsider the very fundamentals of how small planetary bodies live and die. It suggests that the ingredients for a dynamic world are more diverse and surprising than we ever imagined, involving not just internal chemistry but also gravitational dances and celestial collisions. The silent moon, it turns out, was once a world of immense hidden power, and we are only just beginning to understand how it worked. Leaving the familiar confines of the inner solar system, we venture out to the realm of the gas giants, where a moon orbits that looks less like a natural satellite and more like a carefully crafted piece of cosmic art. Circling Saturn is Iapetus, a world of stark contradictions. One hemisphere is as dark as fresh asphalt, the other as bright as dirty snow, creating a yin-yang effect that is visually stunning. But its most jaw-dropping feature is a ridge that defies all logic, a mountain range that runs with near-perfect precision along the moon's equator, stretching over 1,300 kilometers long, and in places soaring to heights rivaling Mount Everest. This isn't a random collection of peaks. It's a singular, continuous, and almost artificial-looking structure that gives Iapetus the unmistakable appearance of a colossal walnut spinning through the void. The sheer scale and precision of this ridge is what makes it so utterly baffling. How does a natural process create a feature so symmetrical, so perfectly aligned with the equator, on a world that is only about 1,500 kilometers in diameter? There is no known geological mechanism on any other planet or moon that produces anything quite like it. It's as if some cosmic tailor stitched a seam exactly around Iapetus's waist. This has, of course, led to a host of theories, each more fascinating than the last, and yet none has achieved universal acceptance. One of the leading ideas suggests that Iapetus was once surrounded by a ring system of its own, much like its parent planet, Saturn. In this scenario, the moon would have formed with a disk of debris circling it. Over time, the gravitational pull of Iapetus would have drawn this material inward, causing it to rain down onto the surface. But because the particles would have been orbiting in the equatorial plane, they would have accreted in a narrow band around the equator, piling up to form the massive ridge we see today. It's an elegant concept, but it faces a significant hurdle. The ridge material appears to be primarily made of water ice, the same substance that makes up the rest of the Moon's crust, not necessarily foreign material from a former ring. Another compelling theory looks inward, proposing a dramatic and rapid change in the Moon's rotation billions of years ago. Early in its history, Iapetus may have been spinning much faster than it does today. This rapid rotation could have generated immense centrifugal forces, causing the Moon to bulge significantly at its equator. As its spin gradually slowed due to tidal forces, this equatorial bulge would have frozen in place, leaving behind a permanent fossil feature, a frozen monument to its more dynamic youth. While this explains the location, the incredible height of the ridge remains a challenge for this model. Perhaps the most exotic hypothesis involves internal processes. Some scientists have modeled the possibility that the ridge formed through a limited period of intense volcanic activity, but unlike the lava flows we know on Earth, this would have been an eruption of water, a cryovolcanic event on a staggering scale. Imagine geysers of slushy ice erupting along a weak point in the crust of the equator and freezing into a massive ridge. Yet, the global uniformity of this feature makes a singular volcanic event seem unlikely. The mystery of Iapetus's ridge is a beautiful example of how a single, strange feature can force us to reconsider entire planetary processes. It stands as a testament to a violent and creative period in solar system history whose rules we are still struggling to decode. With no future missions currently planned to return to this distant moon, the equatorial ridge of Iapetus remains one of the solar system's most captivating and unresolved architectural wonders, a silent question mark hanging in the Saturnian sky. From the sculpted moon Iapetus, we now turn our attention back to Earth, to a mystery that literally shook our world. On the morning of June 30th, 1908, in a remote part of Siberia near the Podkamennaya Tunguska River, something extraordinary happened. A man sitting on the front porch of a trading post was hurled from his chair as the ground shook violently. The sky split apart with a searing blue light, followed by a series of deafening thunderous booms that were heard hundreds of miles away. The event was so powerful that it created an atmospheric shockwave that circled the globe twice, and for nights afterwards, the skies over Europe and Asia were so bright that people could reportedly read newspapers outdoors at midnight. When expeditions finally reached the epicenter years later, they found a scene of almost unimaginable devastation. 80 million trees had been flattened in a radial pattern over an area of 2,000 square kilometers, all pointing away from the center of the blast. But at the very center of this destruction zone, the trees were not burned to ash as one might expect. They were still standing, stripped of their branches and bark. They stood like a forest of telegraph poles, a silent testament to a force that came not from below, but directly from above. The central, enduring mystery of Tunguska is not the power of the explosion, which is estimated to have been nearly 200 times more powerful than the atomic bomb dropped on Hiroshima. The true puzzle lies in what is missing. Despite this being the largest impact event in recorded human history, there is no crater. No sizable fragments of a meteorite or comet have ever been conclusively found. The leading theory for decades was that a stony asteroid, roughly 50 to 80 meters across, entered Earth's atmosphere at a shallow angle and exploded in a massive airburst several kilometers above the ground. The heat from the compressional shock of its hypersonic travel and the sudden stress of hitting dense air would have caused it to vaporize catastrophically, releasing all of its immense kinetic energy at once in a flash of heat and a hammer blow of pressure. This would explain the radial tree fall and the lack of a crater, but the lack of any meteoritic debris has always been a nagging problem for the asteroid hypothesis. This has led many scientists to champion an alternative theory, that the culprit was not a rocky asteroid but a comet, A comet, being composed primarily of ice and dust, would behave very differently. It could have barreled into the atmosphere and disintegrated even more completely, leaving virtually no solid material behind. The ice would have vaporized instantly, and the dust would have been scattered high into the atmosphere, potentially explaining the anomalously bright nights that followed the event. The comet theory elegantly solves the no fragments problem, but it introduces another: timing. The event happened during the Beta Taurid meteor shower, which is associated with Comet Encke. Could a large fragment have broken off from this known comet and been on a collision course with Earth? It's a compelling cosmic coincidence. More exotic explanations have been proposed over the years, from a microscopic black hole passing through the Earth to the annihilation of a chunk of antimatter. While these are fascinating thought experiments, they lack any supporting evidence and are generally dismissed by the mainstream scientific community. The most likely answer remains a celestial impactor, but the debate over its fundamental nature, rocky asteroid or icy comet, rages on. The Tunguska event is a chilling reminder of our planet's vulnerability. It demonstrates that a city-sized area can be utterly obliterated without a single piece of the impactor ever reaching the ground. If the event had occurred just a few hours later, the rotation of the Earth would have placed a major population center like St. Petersburg or Stockholm in its path, with catastrophic loss of life. Tunguska stands as a silent warning from history, a monument to a force we still don't fully understand, emphasizing our urgent need to map the thousands of near-Earth objects that could one day follow the same path. From the shattered forests of Siberia, we now travel outward to a storm so vast it could swallow our entire planet whole. For centuries, astronomers have trained their telescopes on Jupiter and witnessed its most famous feature: a churning, swirling maelstrom of crimson gas known as the Great Red Spot. This is not merely a cloud formation, it is the solar system's most monumental hurricane, a tempest that has raged continuously since it was first clearly observed in the 1600s. Its sheer longevity is a marvel in itself, but its recent behavior has added a new layer of profound mystery. We are watching this giant storm shrink. Measurements show its width has diminished by more than half over the past century, transforming from a wide oval that could easily fit 3 Earths side by side to a more compact, almost circular vortex that might now only accommodate our planet once. Yet, even as it contracts, it refuses to die. This paradoxical act of shrinking while strengthening defies our basic understanding of fluid dynamics and planetary weather, forcing us to ask what incredible forces are at work deep within Jupiter's alien atmosphere. The first mystery lies in its very existence. On Earth, even the most powerful hurricanes are fleeting phenomena, drawing their energy from warm ocean water and dissipating within days or weeks once they move over land or cooler seas. Jupiter has no solid surface, no oceans to act as a battery. So what is the engine that has powered this storm for 400 years? The answer seems to lie in the complex, layered nature of the gas giant itself. Jupiter is a world of extreme contrasts. Its colorful banded clouds are part of a ferocious jet stream system, with winds screaming in opposite directions at speeds exceeding 600 kilometers per hour. The Great Red Spot is pinned between 2 of these opposing jet streams, acting as a massive atmospheric wheel that rotates counterclockwise, caught in a perpetual tug of war between these powerful winds. This constant shear helps to keep it spinning, but it doesn't fully explain its staggering endurance. The storm's incredible depth provides a crucial clue. Data from NASA Juno spacecraft, which has been peering beneath the cloud tops with its microwave and gravity instruments, revealed that the Great Red Spot is not a shallow weather feature. It is a colossal structure that plunges hundreds of kilometers down into the planet's atmosphere, much deeper than anyone had previously suspected. This profound depth suggests the storm is rooted in processes far below the visible cloud decks, perhaps tapping into internal heat rising from Jupiter's scorching hot interior. This internal energy, left over from the planet's formation and released by the slow compression of gravity, may provide the continuous power source that terrestrial storms lack. It's as if the storm has its own deep-seated geothermal power plant, allowing it to outlive any weather system on a rocky planet. Now add the puzzle of its shrinkage and intensification. As the storm has contracted, its winds have actually increased in speed around its outer edges. Think of a figure skater pulling their arms in to spin faster. The storm appears to be conserving its angular momentum, becoming a tighter, more concentrated vortex. But why is it shrinking at all? One theory suggests it is encountering more atmospheric obstacles as it drifts slowly within the turbulent jet streams, losing energy and material to smaller eddies that break off from its sides. Another idea posits that changes in Jupiter's internal heat flow or the chemistry of the clouds that give the spot its famous color could be altering its stability. The red hue itself is a mystery, possibly caused by complex hydrocarbons like ammonium hydrosulfide or organic compounds called tholins being dredged up from deeper, warmer layers and broken apart by solar ultraviolet radiation. The great red spot's stubborn persistence amid its transformation makes it a unique natural laboratory. It challenges us to understand how energy is transferred across vast scales in a fluid environment utterly unlike our own. Is the storm we see today the same one observed by Galileo's contemporaries, or is it a self-sustaining phenomenon that can regenerate itself, a permanent feature of Jupiter's atmospheric machinery that merely changes form over epochs? We simply do not know if its current shrinkage is a prelude to its eventual disappearance or just the latest phase in an endless cycle of transformation. By studying this ancient, enduring storm, we are not just learning about Jupiter, we are deciphering the fundamental rules that govern atmospheres everywhere, including those on the exoplanets we are discovering around distant stars. The Great Red Spot is a timeless sentinel, a whirling vortex of secrets that has watched over the solar system for centuries, and it is not ready to give them up just yet. But as we marvel at Jupiter's enduring storm, its ringed neighbor Saturn presents an atmospheric puzzle that is, if anything, even more geometrically perfect and baffling. Imagine a hurricane, but one shaped not like a swirling circle, but like a precise six-sided hexagon with each side longer than the diameter of Earth. This is not a CGI creation or an optical illusion. It is a real, persistent feature spinning around Saturn's North Pole, a piece of cosmic geometry so exact it seems almost artificially crafted. First glimpsed by the Voyager probes in the 1980s, this staggering formation was thought to be a fleeting oddity until NASA Cassini spacecraft arrived decades later and found it not only still there but virtually unchanged, a permanent and monumental fixture in the Saturnian sky. The sheer scale of the hexagon is difficult to comprehend. Each of its 6 sides stretches nearly 14,000 kilometers across, making the entire structure wide enough to fit 4 Earths side by side inside it. And it is not a static cloud pattern, it is a raging jet stream, a river of air hurtling along its boundaries at speeds exceeding 320 kilometers per hour. At its center lies a massive, rotating storm, but the hexagon itself acts as a barrier containing the chaotic weather within its strikingly straight walls. The fundamental mystery is right there in its shape. How does nature, which tends to favor spirals, spheres, and swirls, produce something with such sharp, consistent angles on a planetary scale? The prevailing theory among atmospheric scientists involves something known as standing wave patterns. The idea is that deep within Saturn's fluid atmosphere, there are layers rotating at different speeds. This creates shear and turbulence which can generate waves. If you've ever seen a perfectly shaped ripple form on a pond or watched a guitar string vibrate at a specific frequency to create a stable note, you've witnessed a standing wave. Scientists propose that Saturn's hexagon is a massive planetary-scale version of this phenomenon, a particular type of wave called a Rossby wave, which is associated with the rotation of a fluid body and the variation of forces within it, could be responsible. The mathematics suggest that under the right conditions, such a wave can get trapped at a specific latitude, in this case Saturn's North Pole, and manifest as a polygonal shape, with a hexagon being a particularly stable configuration given the planet's specific rotational speed and atmospheric depth. Computer modeling has had some remarkable success in recreating this effect. In laboratory experiments, when a fluid is spun rapidly in a circular tank, different polygons, including hexagons, can spontaneously emerge at the center. When researchers input data based on Saturn's conditions into sophisticated atmospheric models, they can generate a stable, rotating hexagon. This provides a powerful, if not yet definitive, argument for a natural origin. The hexagon, according to this view, is a colossal atmospheric fingerprint, a visible manifestation of the deep, hidden physics governing the planet's churning interior. Yet, even with these compelling models, the Saturn hexagon retains its aura of mystery. The astonishing longevity and stability of the shape is what continues to astound researchers. The laboratory experiments and computer simulations show that these polygonal waves can form, but they are often transient and unstable. Saturn's hexagon has persisted for decades, and likely much longer, weathering the immense dynamic forces within a gas giant's atmosphere without losing its geometric perfection. This suggests there are stabilizing factors we have yet to identify or fully understand. The incredible depth of Saturn's atmosphere, revealed by Cassini to extend thousands of kilometers downward, likely plays a crucial role, providing a deep anchor for this swirling pattern that we can only see at the cloud tops. Furthermore, the hexagon is not a monolith, it is a dynamic system. Cassini's infrared and visible light cameras revealed that the structure changes color with Saturn's seasons, shifting from a bluish hue to a more golden brown as sunlight increased over the northern hemisphere's 7-year-long spring. This indicates complex chemistry and the movement of aerosols and particulates being churned by the powerful winds, all contained within the hexagon's stark boundaries. The precise, unwavering geometry acts as an invisible wall, orchestrating the chaos within it into a breathtakingly ordered display. This enduring enigma reminds us that the laws of physics can produce patterns of beauty and precision far beyond our everyday experience, a signature written in clouds and wind that we are only just beginning to decode. Across the solar system, another giant world holds a tilt so extreme it redefines our very notion of a planetary season. While Earth enjoys a modest 23.5-degree lean, giving us the gentle rhythm of spring, summer, fall, and winter, Uranus is a world that has essentially fallen over. Its rotational axis is tilted a staggering 98 degrees relative to its orbit around the Sun. This means Uranus doesn't so much spin as it does roll around the Sun like a cosmic billiard ball, with its poles taking turns pointing directly at our star. The result is the most extreme seasonal cycle we know of. For 21 Earth years, one pole of Uranus is bathed in continuous, direct sunlight, a perpetual summer day, while the other hemisphere is plunged into a deep, frigid winter night of total darkness that lasts for 2 full decades. Then, over the course of its 84-year orbit, the roles reverse. The prevailing theory for how Uranus ended up in this bizarre orientation is as dramatic as the tilt itself. Most planetary scientists believe that in the chaotic early days of the solar system, a protoplanet, a world in its own right, at least the size of Earth and possibly even larger, slammed into the young Uranus in a cataclysmic grazing collision. This wasn't a simple impact that left a crater. It was a blow so devastating that it literally knocked the planet onto its side, forever altering its fundamental spin. The energy from such an impact would have been truly apocalyptic, likely vaporizing the impactor and liquefying much of Uranus's interior, scattering a tremendous amount of debris into space. Some of that debris may have later coalesced to form the planet's family of moons and its dark, narrow rings, which all share the planet's extreme orbital inclination, orbiting around its waist like hula hoops around a tilted dancer. This single ancient event would have set the stage for the strange world we see today, but the tilt is only the beginning of the mystery. This profound lean creates a magnetic field that is just as bizarre and off-kilter. Unlike the relatively orderly magnetic fields of Earth, Jupiter, or Saturn, which are roughly aligned with their rotational axes, the magnetic field of Uranus is a lopsided mess. Its magnetic poles are offset from its geographic poles by almost 60 degrees, and the field itself doesn't even emerge from the planet's core. Instead, it appears to be generated in a salty, electrically conductive layer of water and ammonia deep within the icy mantle, a slushy ocean under immense pressure. Because of the planet's extreme tilt, this magnetic field is twisted into a complex, corkscrewing shape that tumbles wildly through space as the planet rotates. Imagine trying to navigate with a compass that doesn't point north, but instead spins in chaotic circles, and you begin to understand the challenge of understanding Uranus's magnetosphere. When the Voyager 2 spacecraft flew past in 1986, it happened to be during the planet's southern summer with the South Pole aimed at the Sun. This meant the magnetic field, with its bizarre orientation, was presented to the solar wind in a way we have never seen on any other planet. The results were startling. The magnetosphere was opening and closing like a lazy, rotating lighthouse beam, allowing solar wind to pour in and interact with the atmosphere in unpredictable ways. This unique magnetic dance, combined with those 42-year-long seasons, creates an atmospheric environment unlike any other. The hemisphere, baking in decades of sunlight, might be expected to warm up significantly, but Uranus's weather system seems oddly muted and sluggish compared to the violent storms of Jupiter or Saturn, adding another layer to its enigma. We are left with a world shaped by a single, violent moment in deep time. A tilted giant whose hidden, sloshing interior generates a magnetic field that defies easy classification, making Uranus one of the most profoundly strange and least understood planets in our entire solar system. And so we arrive at perhaps the most perplexing sibling rivalry in our solar system, a tale of two nearly twin worlds with wildly different personalities. Uranus and Neptune are often grouped together as ice giants, two distant blue orbs of similar size, mass, and atmospheric composition. They are cosmic cousins formed from the same primordial soup of ice, rock, and gas at the outer edges of the primordial solar nebula. And yet, when we take their temperature, a profound and fundamental difference emerges, one that points to a deep, burning mystery within Neptune's core. While Uranus is a remarkably lukewarm world, radiating back into space almost exactly the same amount of energy it soaks up from the distant sun, Neptune is a world ablaze with internal fire. It emits 2.6 times more energy than it receives from our star. This means that for every single watt of solar power that reaches its cloud tops, Neptune generates and releases nearly 2 more watts from some hidden, powerful source deep within its heart. This is not a small discrepancy, it is a chasm, a glaring clue that beneath its serene blue exterior, Neptune is a world of immense and hidden dynamism. This surplus energy has direct and visible consequences. It acts as the primary engine for the most ferocious weather in the solar system. Despite being the planet farthest from the sun and receiving the least amount of solar heating, Neptune boasts wind speeds that dwarf every other world, with hurricanes screaming across its atmosphere at over 2,000 kilometers per hour. These are supersonic winds powered not by the faint warmth of the sun, but by the tremendous heat welling up from the planet's interior. This internal furnace creates massive convection currents, driving the churning of its atmosphere and sculpting the brilliant white cloud features that race around the planet. The Great Dark Spot observed by Voyager 2 was a testament to this power, a storm the size of Earth that appeared and vanished, a fleeting signature of the turbulent energy burning within. The question that has baffled planetary scientists for decades is a simple one. What is the source of this immense power, and why does its twin, Uranus, seemingly lack it? One of the most captivating and poetic theories proposed to explain this internal heat is the concept of diamond rain. The interiors of these ice giants are realms of almost unimaginable pressure and temperature. Deep beneath the outer layers of hydrogen and helium, there is believed to be a vast, superhot and superdense ocean of water, ammonia, and methane ices. Under these extreme conditions, the methane, a molecule made of one carbon atom bonded to 4 hydrogen atoms, can be shattered. The carbon atoms, freed from their bonds, are then squeezed together with such incredible force that they crystallize, forming actual diamonds. These diamonds, heavier than the surrounding slushy material, would then sink in a glittering, continuous shower towards the planet's core. This constant downward hail of diamonds is more than just a beautiful thought. It is a physical process that releases gravitational energy. As the dense diamonds fall, they convert potential energy into kinetic energy and ultimately, through friction, into heat. This heat then slowly migrates upward over millions of years, finally escaping into space as the radiant energy we detect. It's a stunning idea that the shimmer of a diamond on Earth originates from a process where entire storms of them fall perpetually in the heart of a distant planet. While lab experiments using powerful lasers have successfully recreated the conditions needed to form nanodiamonds from methane, confirming the physics is plausible, we still don't know if this process generates enough continuous heat to account for Neptune's massive energy surplus. Other theories delve deeper into the planet's formation. It's possible that Neptune simply retained more of its primordial heat of formation, the incredible energy released when trillions of tons of planetesimals crashed together to build the planet. This heat would be very slowly leaking out over billions of years, but this raises the obvious question: why would Uranus, a planet of nearly identical mass and composition, have lost its heat so completely? The answer might lie in the same colossal impact that is thought to have knocked Uranus onto its side. That catastrophic collision could have been so violent that it effectively shattered the planet's core, stirring it up and allowing a huge amount of that trapped formation heat to escape in a relatively short geological time, leaving Uranus thermally depleted. Neptune, by contrast, may have avoided such a traumatic event, allowing its interior to remain stratified and better insulated, letting its heat leak out at a much slower and steadier pace. This would make Neptune's excess heat not an anomaly, but the standard for an ice giant, with Uranus being the odd one out due to its violent past. A third possibility involves the differentiation of heavy elements within the core. As the planet cools over eons, heavier elements and compounds might be slowly sinking toward the center, while lighter material rises. This gradual gravitational sorting also releases energy, contributing to the internal heat flow. The precise composition and structure of Neptune's core, something we have barely begun to understand, would dictate how significant this process is. Without a dedicated mission to orbit these distant worlds and probe their deep interiors with gravity science and seismology, the mystery of Neptune's fiery heart remains wide open. It is a powerful reminder that a planet's history is written not just on its surface, but in the secret, energetic processes happening deep within. Processes that can turn a frozen world at the edge of darkness into a cauldron of heat and storm. Far beyond the orbit of Neptune, in the deep freeze of the Kuiper belt, a world we once thought would be little more than a frozen, cratered relic has instead revealed itself to be one of the most geologically vibrant places in the entire solar system. When the New Horizons spacecraft shot past Pluto in 2015, it didn't just send back pictures of a distant dwarf planet, it delivered a portrait of a world that is stunningly, bafflingly alive. And at the very heart of this activity lies a feature so strange and so beautiful it has redefined our understanding of what's possible in the outer solar system: Sputnik Planitia. This vast, heart-shaped plain of nitrogen ice is not a flat, frozen wasteland. Instead, it is broken up into a series of irregular, cell-like polygons, each stretching 10 to 20 miles across and bordered by shallow troughs. From above, it looks less like a natural landscape and more like the cross-section of a beehive or a pan of slowly simmering custard that has just begun to congeal. This is Pluto's greatest mystery, and its existence points to a hidden fire within this icy world. The polygons are the visible signature of a process called convection, a phenomenon we usually associate with much warmer, more dynamic worlds. Here's how it works on Pluto. The surface of Sputnik Planitia is not made of water ice, which would be rock-hard and immobile at Pluto's average temperature of -387 degrees Fahrenheit. Instead, it's a vast sheet of solid nitrogen, a substance that, even at these incredibly cold temperatures, can behave in a surprisingly pliable way. The ice sheet is several miles thick, and the nitrogen at its very bottom is warmed by the faint, lingering heat from Pluto's rocky interior. Even that minuscule amount of warmth is enough to make a critical difference. Because nitrogen ice expands when it warms, this slightly warmer ice at the bottom becomes buoyant. It begins to slowly rise towards the colder surface in great, blobby upwellings. As it rises, it cools, eventually sinking back down along the boundaries between these rising cells. This incredibly slow-motion churning, a complete cycle likely takes hundreds of thousands of years, carves the troughs that form the polygon borders and constantly renews the surface of the plane, erasing any impact craters and leaving it looking impossibly young and smooth. This simple explanation, however, opens up two profound and deeply puzzling questions. The first is one of energy. Where is this internal heat coming from? Pluto is a small world far from the Sun, and it should have lost the heat from its formation billions of years ago. For convection of this scale to be happening today, there must be an active internal heat source keeping the engine running. The most likely candidate is the slow, radioactive decay of elements like uranium and potassium locked within Pluto's rocky core. But the amount of heat this generates is tiny, and whether it's sufficient to power the dramatic convection we see is a major subject of debate. Some scientists have proposed that the heat could be generated by tidal interactions with Pluto's large moon, Charon. The two are locked in a gravitational embrace, always showing the same face to each other. While this orbit is now stable, it may not always have been, and the gravitational flexing during their orbital dance eons ago could have pumped enough energy into Pluto to keep its interior warm for much longer than expected. The second, even more tantalizing mystery is what lies beneath Sputnik Planitia itself. The convection cells are not scattered randomly, they are organized across the entire basin with an eerie uniformity. This suggests that the ice sheet has a remarkably consistent thickness and is being warmed from below in an extremely even way. Many planetary geologists believe this is no accident. The leading theory is that Sputnik Planitia is a massive impact basin, much like the ones on our moon, but one that was later filled to the brim with nitrogen ice. The impact that created it would have been cataclysmic, blasting away a huge portion of Pluto's crust. This event left behind a thin spot in the global crust and, crucially, may have left a blob of heavier material sitting far below the surface. This subterranean mass deficit could be acting as a gravitational anchor, perfectly aligning the entire feature with the tidal axis between Pluto and Charon. The constant churning of the nitrogen ice, then, is not just a curious geological quirk, it is the surface expression of a deep planetary wound, a window into Pluto's violent history and its unexpectedly dynamic present. This distant, tiny world is not the dead rock we imagined, but a complex geological entity, whispering secrets about how even the coldest, most remote places in our solar system can harbor surprising and beautiful forms of activity. Yet, even as we marvel at the dynamic geology of a distant dwarf planet, another small world much closer to home has been silently flaunting one of the most visually arresting mysteries in the entire asteroid belt. When NASA's Dawn spacecraft arrived at the dwarf planet Ceres in 2015, its cameras immediately spotted something that shouldn't be there. Scattered across the dark, heavily cratered surface were dozens of intensely bright, almost shimmering spots, with the most brilliant cluster sitting at the heart of a 57-mile-wide crater named Iapetus. From a distance, these gleaming patches looked like a city's worth of light shining up from the darkness, an illusion so compelling it sparked a wave of excited speculation. But the truth, revealed by Dawn's gradual descent into lower orbits, was far stranger than any science fiction. These weren't lights, they were vast deposits of salt, gleaming with an almost painful brightness under the weak light of the distant sun. The composition of these brilliant spots was the first major clue. Dawn's spectrometer identified the material as sodium carbonate, a kind of salt commonly found in evaporative deposits on Earth, like the crusty shores of a dried-up lake. Finding it here in such concentrated and reflective patches was a staggering revelation. Sodium carbonate doesn't just appear on the surface by itself. It is a calling card left behind by briny, mineral-rich water. This discovery immediately suggested that Ceres, a world once written off as a primitive and frozen relic, is anything but dead. It possesses a complex, watery interior that has, at various points in its history, found a way to breach the surface. The central mystery of Iapetus crater is not what the bright spots are, but how this salty sludge managed to get there in the first place. Scientists have since been piecing together a dramatic story of a recent and violent geologic past. The most widely accepted theory begins with a colossal impact. A large asteroid slammed into Ceres, blasting out the Iapetus crater and fracturing the rocky crust deep beneath it. This impact created a network of cracks and flaws that tapped into a vast subsurface reservoir of salty, liquid water. Relieved of pressure, this buried brine began to force its way upward. In a process known as cryovolcanism, the frigid, mud-like mixture erupted onto the surface not as scorching lava, but as an icy slush. This slush would have spread across the crater floor, where the water component quickly sublimated in the near vacuum, turning directly from ice into vapor and vanishing into space. What was left behind was a gleaming, expansive deposit of pure sodium carbonate and other salts, a permanent salt stain marking the site of this incredible eruption. But the story doesn't end with a single ancient event. The stunning brightness of the largest deposit, named Cerealia Facula, is itself a major clue. In the airless environment of space, surface materials are constantly bombarded by micrometeorites and solar radiation, a process called space weathering that gradually darkens them over time. The fact that these salt deposits are still so brilliantly white suggests they are remarkably young, geologically speaking. Some estimates place their age at a mere 4 million years, a blink of an eye in the 4.5 billion-year history of the solar system. This raises the electrifying possibility that the process that created them might not be over. The reservoir of brine deep beneath Iapetus crater might still be there, perhaps even still active, occasionally venting fresh material to renew the bright spots and keep them shining. The implications of this are profound. Ceres is now understood not as a simple ball of rock and ice, but as an ocean world in its own right, a member of a club that includes Europa and Enceladus. It likely contains a global layer of briny water, sandwiched between its rocky core and icy mantle. The Iapetus crater bright spots are our best evidence that this ocean isn't completely isolated. It can sometimes interact with the surface, bringing its chemistry into the light. This makes Ceres a fascinating candidate in the search for life beyond Earth. While its subsurface ocean may be colder and saltier than those on the icy moons of the gas giants, it contains the key ingredients thought to be necessary for biology: liquid water, a source of heat from radioactive decay, and a rich chemical soup of organic compounds that Dawn also detected on the surface. The gleaming spots of Iapetus crater are more than just a pretty anomaly. They are a beacon pointing us toward the hidden, watery secrets of the largest world in the asteroid belt. But our journey into the solar system's fringes is far from over, and the next mystery forces us to look beyond the familiar planets and dwarf planets to the very edge of our sun's influence, to a region known as the Kuiper Belt. This vast disk of icy remnants stretching out beyond Neptune's orbit is often described as a more distant and much larger cousin to the asteroid belt. For decades, we pictured it as a relatively smooth, gradually thinning cloud of frozen objects, a gentle conclusion to the planetary part of our solar system. However, as our telescopes have grown more powerful and our surveys more complete, we've discovered that the outer boundary of this belt is not a gentle fade into the darkness of interstellar space. Instead, it is a cliff, a sudden, dramatic, and utterly perplexing drop-off in the number of objects, as if someone took a cosmic knife and sheared away everything beyond a certain specific point. This isn't a small-scale feature, it's a fundamental characteristic of our solar system's architecture. The vast majority of Kuiper Belt objects, or KBO, are found within a band that ends abruptly at about 50 astronomical units from the Sun. That's 50 times the distance from Earth to the Sun. Beyond this line, the population of objects plummets. The few icy bodies we do find farther out, like the dwarf planet Sedna, are rare exceptions on wildly unusual orbits, not part of a continuous population. This sharp edge is one of the most significant unsolved problems in modern planetary science because, according to our standard models of how the solar system formed, it simply shouldn't exist. The primordial cloud of debris from which our planets coalesced should have extended much farther out, thinning gradually for hundreds of astronomical units. The presence of this cliff implies that something powerful, something we haven't yet seen, violently sculpted the outer solar system and carved off this material. Scientists have put forward two primary and equally dramatic explanations for this cosmic amputation. The first, and perhaps most famous, is the Planet 9 hypothesis. This theory proposes that a previously undetected planet, a true super-Earth or mini-Neptune up to 10 times the mass of our own world, is orbiting the Sun hundreds of astronomical units away on a highly elongated path. The gravitational influence of this massive, distant world could be shepherding the Kuiper Belt, herding most objects inward and clearing out a vast swath of space beyond its own orbit. Its gravity would act like a celestial plow, pushing and pulling on these smaller icy bodies over billions of years, either flinging them into the Sun, ejecting them from the solar system entirely, or shepherding them into clustered orbits that avoid its gravitational domain. This would neatly explain not only the Kuiper Cliff, but also the peculiar, clustered orbits of some extreme trans-Neptunian objects that all seem to point toward a common, unseen source of gravitational perturbation. The second major theory reaches beyond our Sun entirely, proposing a stellar intervention in our solar system's infancy. Billions of years ago, when our star was still nestled within its natal cluster alongside thousands of other newborn stars, a close flyby from a sibling star is not just possible but statistically likely. The gravitational tide from a passing star could have ripped away the outer material of our protoplanetary disk, stripping the Kuiper Belt down to its current sharp edge and stealing a vast cloud of comets to carry off into interstellar space. This event would have been a moment of incredible violence, a gravitational encounter that fundamentally shaped the inventory of our solar system in a single celestial moment. In this scenario, the Kuiper Cliff is not an active, ongoing phenomenon but a fossilized relic, a permanent scar from a traumatic close call that occurred over 4 billion years ago. Each theory has its strengths and its challenges. The Planet 9 hypothesis is compelling but requires us to find a needle in a cosmic haystack, a dim, cold, incredibly distant world that has so far eluded every dedicated search. The stellar flyby theory elegantly fits the data but is ultimately untestable, as the sibling star that might have caused it is long gone, lost among the hundreds of billions of stars in the Milky Way. The true answer might even lie in a combination of these events, or in a process we haven't yet conceived. What makes the Kuiper Cliff so captivating is that it is a silent, invisible boundary that speaks volumes about the hidden forces and violent history that have shaped our cosmic neighborhood. It is a stark reminder that the solar system does not end with Pluto or even the Kuiper belt. It extends into a realm of darkness and mystery, where the rules we think we understand may be rewritten by a giant, unseen world or the ghost of a stellar encounter from the dawn of time. And just when we thought we had mapped the boundaries of our own solar system, the universe decided to send us a visitor from the great beyond, an object that challenged our very definitions and ignited a firestorm of scientific debate. In October 2017, the Pan-STARRS telescope in Hawaii detected a faint point of light moving at breathtaking speed. Its trajectory was immediately and shockingly clear. This was no asteroid or comet from our own solar system. It was the first interstellar object ever observed passing through our cosmic neighborhood, and it was given a name befitting its historic nature, Oumuamua, a Hawaiian term meaning a messenger from afar arriving first. Everything about Oumuamua was strange from the very beginning. As it hurtled away from the sun after its slingshot around our star, telescopes around the world scrambled to study it. They determined it was long gone, already speeding back out into the depths of interstellar space, but the data it left behind was profoundly puzzling. Its light curve, the way its brightness changed over time, was extreme. It varied in brightness by a factor of 10 as it tumbled end over end, a telltale sign that it must be dramatically elongated. The best models suggested a shape unlike anything we see in our own solar system, a cigar or a pancake, perhaps 5 to 10 times longer than it was wide. This alone made it a fascinating oddity. But then came the real mystery, the one that truly set the astronomical world alight. As Oumuamua departed, it did something utterly unexpected. It accelerated. This was not the gentle, predictable coast of an object governed solely by the sun's gravity. Instead, its speed increased in a way that could not be explained by gravitational forces alone. It was as if it had a tiny, extra engine pushing it from behind. For a comet, this behavior would be commonplace. Ices on a comet's surface warm as it approaches the sun, turning directly into gas in a process called outgassing. This venting material acts like a thruster, giving the comet a non-gravitational kick. The critical, glaring problem with Oumuamua was that it showed no visible signs of outgassing. There was no coma, the fuzzy envelope of gas and dust that surrounds a comet's nucleus, and no detectable tail of debris streaming behind it. It was as dark and featureless as a rotating cinder in every observation. So if it wasn't outgassing like a normal comet, what was causing this precise and measurable acceleration? The scientific community split into camps, each proposing a natural explanation for this bizarre push. The leading hypothesis, and the one most astronomers find most plausible, is that Oumuamua was indeed a comet, but a very exotic one. It could have originated around another star composed of ices we're less familiar with, such as solid hydrogen or solid nitrogen. As the sun's heat warmed it, these exotic ices could have sublimated, turning directly from a solid to a gas without leaving the dusty debris trail that water ice creates. This pure gas emission might have been invisible to our telescopes, but it would have provided just enough thrust to account for the acceleration. Alternatively, it could have been a more standard comet that had spent eons being bombarded by cosmic radiation in the emptiness of interstellar space, building up a thick, carbon-rich crust that sealed its more volatile ices inside. When the sun warmed it, the ices beneath this hard shell could have vented through specific jets, again providing thrust without releasing large amounts of visible dust. Yet, the object's peculiar shape and the lack of any visible activity led others, most notably Harvard astronomer Avi Loeb, to propose a far more speculative and captivating idea, that Oumuamua could be a piece of alien technology, perhaps a light sail, a thin, reflective sheet designed to be pushed by the radiation pressure from stars. In this scenario, its unusual acceleration would be explained not by outgassing, but by the gentle, constant push of sunlight itself against its vast, flat surface. Its tumbling motion could be attributed to it being a derelict, a discarded piece of a much larger vessel floating aimlessly through the galaxy. While this idea is thrilling, the vast majority of the scientific community maintains that an extraordinary claim requires extraordinary evidence, and that all of Oumuamua's oddities, while unusual, can still be explained by natural phenomena we just haven't observed up close before. The profound frustration is that we will likely never know for sure. Oumuamua is now far beyond the reach of any current spacecraft, a silent envoy disappearing forever into the dark. Its fleeting visit left us with more questions than answers, a single day to point from the vast galaxy that forces us to wonder about the true nature of interstellar objects. Was it a strangely shaped comet with a unique composition, a fragment of a Pluto-like world ripped from another star system, or something even more incredible? Its legacy is not a solution but a catalyst. It taught us that interstellar visitors are likely common, and it spurred the development of new projects like the Vera C. Rubin Observatory, designed to find more of them. Oumuamua is a permanent celestial mystery, a reminder that sometimes the most profound discoveries are the ones that vanish before we can fully understand them, leaving us to forever ponder what might have been. But even as we grapple with the fleeting enigma of interstellar visitors, the gravitational pull of our own solar system's deepest mystery calls us back to a darkness so profound it may hide an entire world. The evidence for this hidden giant does not come from a direct photograph or a shimmer in a telescope. It is written in the skewed paths of tiny, frozen worlds billions of miles away. This is the captivating hunt for Planet 9, a hypothetical world whose existence is inferred solely from the gravitational whispers of its distant neighbors. The story begins not with a new discovery, but with a pattern recognized in the chaos. Astronomers studying the orbits of extreme trans-Neptunian objects, those that swing far beyond Neptune on long, elliptical journeys, noticed something peculiar. The most distant of these icy bodies, like Sedna and a handful of others, don't have random orientations. Instead, their orbits are clustered together, their points of closest approach to the Sun all grouped in a similar region of the sky, and their orbital planes tilted in a similar way. This is the celestial equivalent of several different compass needles all pointing in the same direction despite being scattered across a table. In a randomly distributed Kuiper belt, this degree of clustering should be incredibly rare, a statistical fluke with odds of less than 0.01%. This bizarre alignment suggests something massive is out there, herding them, its immense gravity acting as an invisible shepherd guiding their paths. The hypothetical planet needed to explain this shepherding effect would be a true giant, a world with a mass estimated at 5 to 10 times that of Earth. This would place it in the category of a super-Earth or a mini-Neptune, a type of planet that is incredibly common around other stars but conspicuously absent from our own solar system unless, of course, it's been hiding in the shadows all along. Its orbit would be equally colossal and elongated, taking it on a staggering 10,000 to 20,000-year journey around the Sun. At its closest approach, it might come within 200 astronomical units of the Sun, but at its most distant, it could swing out nearly 1,000 astronomical units into the frigid blackness. This incredible distance is the primary reason it has evaded detection for so long. At such a remote outpost, the Sun would be little more than a particularly bright star in its sky, providing almost no illumination. Any light from the sun that did manage to reflect off its surface would take over a week to travel back to our telescopes, arriving as an unimaginably faint and sluggish photon. Spotting it is the ultimate cosmic needle in a haystack challenge, requiring us to scan vast swaths of the sky for a single, barely moving pixel of light. The search for this elusive world is a testament to both human ingenuity and patience. Teams of astronomers are using some of the most powerful telescopes on Earth, like the Subaru telescope in Hawaii, to meticulously photograph the slivers of the sky where the planet's predicted orbit might take it. They take images of the same patch of sky over several nights, looking for any object that moves just a tiny amount against the background of fixed stars. It is painstaking, tedious work sifting through terabytes of data for that one telltale sign. Yet, despite these extensive searches, Planet 9 remains at large. This failure to find it has only deepened the mystery, leading to other, even more exotic theories. Some scientists propose that the gravitational anomalies could be explained not by one large planet, but by the collective pull of a massive disk of small, icy objects that we also haven't seen. Others wonder if the apparent orbital clustering is not real, but an observational bias, a trick of the light caused by the extreme difficulty of finding these objects in the first place. Perhaps we are only looking in the right places to find objects with these aligned orbits, missing a larger population that would make the clustering disappear. The implications of finding Planet 9 would be revolutionary, rewriting the story of our solar system's formation and evolution. Its sheer size and distant orbit suggest it may not have formed where it is now. The leading theory is that it was born much closer to the Sun, alongside the other giant planets, before a gravitational tug of war with Jupiter or Saturn sent it hurtling out into the distant reaches, where it now resides in a stable but lonely orbit. Its discovery would provide a missing link, a captured native sun that explains the current architecture of the outer solar system and connects our own cosmic neighborhood to the plethora of super-Earths we see orbiting other stars. The hunt for Planet 9 is more than a scientific pursuit. It is a thrilling detective story set on the grandest possible scale, a reminder that even in our own celestial backyard, the most monumental discoveries may still be waiting in the dark, their presence felt only through the subtle gravitational tugs they exert on the world we think we know. Yet, even as we scan the distant darkness for a hidden giant, one of the most electrifying mysteries of all emerged much closer to the Sun, within the toxic, crushing embrace of our sister planet. The story begins not with a telescope image, but with a single, startling spike on a spectrograph, a signal that, if confirmed, could forever alter our understanding of life in the universe. In September 2020, a team of astronomers made a bombshell announcement. They had detected the spectral signature of phosphine gas in the cloud decks of Venus. Now on Earth, phosphine is a notoriously foul-smelling and toxic gas, but its significance here is monumental. We know of only two ways it can be produced in large, persistent quantities on a rocky planet. One is through human industrial processes. The other is as a waste product of certain types of anaerobic microbes, tiny organisms that thrive in oxygen-free environments. On Venus, with no factories or digesting cows, the implication was staggering. This gas could be a potential biosignature, a tantalizing hint that microbial life might be floating in the temperate layers of the Venusian atmosphere. The location of this detection is what makes the possibility so hauntingly compelling. The surface of Venus is a true hellscape, with temperatures around 800 degrees Fahrenheit and pressures 92 times those on Earth, conditions that would crush and vaporize any known life form in an instant. But about 50 to 60 kilometers up in the thick cloud layers, the environment is surprisingly almost clement. The temperature and pressure there are remarkably similar to those found on Earth's surface. Of course, the clouds themselves are not made of benign water vapor. They are primarily droplets of sulfuric acid, a highly corrosive substance that would quickly dissolve most organic molecules we're familiar with. This is the central paradox of the phosphine mystery. The environment is simultaneously the most hospitable spot on Venus and yet still unimaginably hostile, a place where any life would have to possess a biochemistry far stranger than anything we have ever encountered. Unsurprisingly, this extraordinary claim triggered an intense and ongoing scientific debate, a rigorous process that is science at its very best. The initial detection was controversial, with other teams reanalyzing the same data and questioning the signal processing methods, suggesting the phosphine signature might be a misinterpretation of a different sulfur compound common in Venus's atmosphere. Subsequent observations have yielded conflicting results, some supporting the original find, others finding nothing at all. This back and forth isn't a sign of failure. It is the essential, painstaking work of verification when the stakes are this high. The fundamental question became, if it is phosphine, and if it's not life, then what incredible geological or chemical process could possibly be producing it in such quantities under those conditions? This launched a frantic search for abiotic or non-biological explanations. The leading alternative theory points to volcanoes. Venus is known to be volcanically active, and certain volcanic eruptions could, in theory, spew phosphorus containing minerals high into the atmosphere. There, in the clouds, these minerals could potentially react with sulfuric acid or other compounds in a previously unknown pathway to form phosphine. The problem is that we have no direct evidence that this specific chemical reaction occurs at the rate required to explain the proposed phosphine levels. It would require a volume of volcanic activity far beyond what we currently believe is happening on Venus. Other ideas have been proposed involving exotic chemical reactions driven by sunlight or lightning, but so far, none have been able to fully account for the signal without requiring a series of unlikely events. The phosphine debate, therefore, remains utterly unresolved, a perfect storm of tantalizing possibility and maddening uncertainty. It highlights the immense difficulty of doing remote science on a world as forbidding as Venus, where a thick, global blanket of clouds stubbornly guards its secrets. This single, contested signal has single-handedly revitalized Venus exploration, pushing it to the forefront of planetary science after decades of being overlooked in favor of Mars and the outer solar system. Multiple space agencies are now developing dedicated missions to return to our twisted sister world, not just to map its surface, but to directly sample its atmosphere. These future probes will fly through the very cloud layers where the phosphine was detected, analyzing their chemistry with instruments designed specifically to sniff out this elusive gas and finally determine its origin. The mystery of Venusian phosphine is more than a debate about a gas. It is a powerful catalyst. It forces us to confront our assumptions about where life can exist and what it might look like, reminding us that the answer to the ancient question, "Are we alone?" might be hiding in the most surprising place of all, right next door. Yet, as we ponder the possibility of life floating in the corrosive clouds of Venus, it forces us to reconsider a fundamental paradox right here on our own planet, a mystery that asks how life ever got a foothold on Earth in the first place. Billions of years ago, when the first single-celled organisms were beginning to stir in the ancient oceans, our Sun was a very different star. Astrophysical models tell us with great certainty that our Sun, like all stars of its type, has been gradually brightening over its lifetime. 4 billion years ago, it was about 30% fainter than it is today. This presents us with a profound and beautiful puzzle known as the faint young sun paradox. If the Sun was so much weaker, its radiant energy too meager to prevent the oceans from freezing solid, then why does the geological record clearly show that Earth had widespread liquid water and even life as far back as 4.4 billion years ago? By all rights, our planet should have been a global snowball, a frozen wasteland incapable of supporting the chemistry of life. The fact that it wasn't suggests that something was acting as a planetary-scale thermostat, keeping the early Earth cozy and warm against the cosmic cold. But what was it? The most intuitive and long-standing solution points to a radically different ancient atmosphere, one choked with powerful greenhouse gases that acted like a thick blanket, trapping the sun's faint heat with incredible efficiency. We know that volcanoes were far more active on the young, geologically vigorous Earth, spewing enormous quantities of carbon dioxide, methane, and water vapor into the air. It's plausible that carbon dioxide levels were hundreds of times higher than they are today, creating a supercharged greenhouse effect that more than compensated for the weak sunlight. This is a compelling and elegant answer, but it runs into a significant problem with the geological evidence. Scientists can analyze ancient rocks like banded iron formations and ancient soils to estimate the partial pressure of carbon dioxide in the primordial atmosphere. While these proxies do indicate higher levels, they often don't show nearly enough to account for the amount of warming required to keep the entire planet ice-free. The math simply doesn't add up. The carbon dioxide blanket on its own seems too thin. This discrepancy has led researchers to propose other, more exotic greenhouse partners that could have worked in concert with carbon dioxide. One leading candidate is methane, a gas produced by early methanogenic microbes. Methane is a far more potent greenhouse gas than carbon dioxide, and a biological source could have provided a powerful, sustainable warming effect once life emerged. Another fascinating theory involves nitrogen. Earth's ancient atmosphere was primarily nitrogen, just like today, but it may have been much thicker, a higher pressure atmosphere overall. A denser nitrogen atmosphere wouldn't be a greenhouse gas itself, but it can amplify the warming effect of other greenhouse gases through pressure broadening, a phenomenon where the molecules are pushed closer together and absorb heat more effectively. Imagine the difference between a thin summer sheet and a thick down comforter. The nitrogen provided the loft, while the carbon dioxide and methane provided the insulation. Perhaps the most dramatic proposal is that Earth's albedo, or reflectivity, was significantly lower. A darker planet absorbs more solar energy. If the continents were smaller and the oceans covered more of the surface, the planet would have been less reflective. Furthermore, the lack of land-based plants means there were no light-colored, reflective leaves, and the sun itself may have emitted a different spectrum of light, with more of its energy in the warming infrared range. There's even a hypothesis that a temporary, super-strong greenhouse effect was triggered by massive asteroid impacts vaporizing rock and releasing immense amounts of steam and carbon dioxide into the atmosphere, creating a short-lived but intense period of warming that could have melted any early ice sheets. The frustrating and beautiful truth is that no single theory provides a perfect, universally accepted solution. The faint young sun paradox endures because it likely wasn't one single factor, but a delicate and dynamic interplay of many different elements: a higher pressure atmosphere, a different mix of greenhouse gases, a lower planetary reflectivity, and perhaps even a slightly brighter young sun than our models predict. It stands as a humbling reminder that our planet's climate is an incredibly complex system, a balancing act between stellar radiation, atmospheric chemistry, geological activity, and even biology itself. Solving this paradox is not just an academic exercise, it is crucial to understanding the precise conditions that allowed life to emerge and flourish. It also provides a critical framework for how we interpret the climates of exoplanets orbiting other stars, teaching us that a faint sun does not necessarily mean a frozen world. The early Earth found a way to stay warm, and in that ancient struggle against the cold lies the very secret of our existence. Yet, as we ponder the paradox of our own planet's warm beginnings, Mars presents us with a modern-day water mystery that is written in fleeting, dark streaks upon its rust-colored slopes. For years, satellite images from orbiters like the Mars Reconnaissance Orbiter have revealed a tantalizing and dynamic phenomenon. On sun-facing slopes, particularly within the planet's deep canyons and crater walls, dark, finger-like streaks appear during the warmer months. They lengthen and darken as temperatures rise, then fade away when the cold returns, only to reappear the following Martian year. These features are known as recurring slope lineae, or RSL, and they became the center of one of the most heated debates in modern planetary science because they offered what seemed like the best evidence yet for liquid water actively flowing on the surface of Mars today. The initial excitement was entirely understandable. The behavior of these streaks screamed liquid water. Their seasonal ebb and flow mirrored the action of groundwater or seasonal meltwater seeping to the surface. Scientists proposed a compelling mechanism. Mars is rich in salts called perchlorates, which are notorious for their ability to drastically lower the freezing point of water. The theory was that these salts present in the Martian soil could interact with tiny amounts of water vapor from the atmosphere or from shallow subsurface ice. When the weak Martian sun warmed the slopes, these hygroscopic salts would pull in that moisture, creating a super salty brine that could remain liquid even at the frigid temperatures far below zero. This brine would then trickle downhill, darkening the soil as it went, creating the streaky patterns we observe from orbit. This wasn't just a geological curiosity, it was a potential habitat. If liquid water, even in the form of a toxic brine, was periodically flowing on Mars, it could be a sanctuary for microbial life, a place where organisms could potentially persist even in the planet's harsh modern environment. This interpretation reached a crescendo in 2015 when NASA held a major press conference to announce the spectral detection of hydrated salts that had water molecules bound within their structure at these RSL sites. It seemed like the smoking gun, the chemical evidence that confirmed the water hypothesis. The announcement captured the world's imagination and strongly influenced the planning for future Mars missions, with rover drivers being instructed to avoid these areas entirely to prevent any potential contamination of these special regions with Earth microbes. However, science is a self-correcting process, and closer scrutiny often complicates the most elegant theories. As researchers gathered more data, the simple water story began to unravel. The biggest blow came from further analysis and new experiments here on Earth. While the hydrated salts were real, their detection didn't necessarily prove liquid water was flowing now. It could just indicate that the salts had absorbed a tiny amount of atmospheric water vapor, a process called deliquescence, without ever forming a flowing brine. More critically, other teams began to point out that the characteristics of these streaks could be explained by a completely dry process. The alternative hypothesis is both simpler and, in some ways, more alien. It suggests that the recurring slope lineae are not caused by water at all, but by the movement of dry, granular material, essentially sand and dust. On Mars, the thin atmosphere and low gravity allow for unique granular flows. The idea is that during the Martian spring and summer, the sun heats these steep slopes, causing frost and snow made of carbon dioxide to sublimate directly from solid to gas at their base. This violent release of gas destabilizes the overlying sand and dust, triggering small avalanches. The dark material falls downhill, revealing the darker substrate below and creating the streaky pattern. As the season changes and the angle of the sun shifts, the process stops, and the brighter dust slowly settles back over the streaks, causing them to fade. This dry avalanche model can accurately replicate the observed behavior and geometry of the RSL in computer simulations without requiring a single drop of liquid water. The debate is far from settled, embodying the very essence of scientific discovery. Proponents of the water hypothesis argue that the dry flow model doesn't perfectly explain all the spectral data or the specific locations where the streaks form. Advocates for the dry model counter that the sheer number of streaks and their occurrence on slopes that are simply too cold, even for a super salty brine, makes the water mechanism physically implausible. The truth may lie somewhere in between, or it may vary from location to location. Some RSL might be driven by dry granular flows, while others, in more favorable microclimates, might indeed involve a transient briny trickle. The mystery of the recurring slope lineae is a perfect example of how difficult it is to interpret a world from hundreds of millions of miles away. It reminds us that Mars constantly challenges our assumptions, offering clues that are tantalizingly familiar yet ultimately alien, forcing us to look beyond our Earth-centric biases to understand the true nature of our enigmatic planetary neighbor. But the story of hidden oceans does not end with the geysers of Enceladus. While that moon offers us a readily accessible sample of a subsurface sea, its larger Jovian cousin presents a mystery that is perhaps even more profound, hidden beneath a shell of ice that has tantalized astronomers for decades. Jupiter's moon Europa, with its smooth, cracked, and youthful surface, has long been the #1 candidate in the search for life beyond Earth. This frozen world is crisscrossed with dark streaks and jumbled ridges, a clear indication of a geologically active interior where the ice crust is constantly being fractured, reworked, and renewed. For years, the strongest evidence for its subsurface ocean was indirect: the way its surface flexes under Jupiter's immense gravitational pull, and the measurements of its own magnetic field, which suggested a global, salty, electrically conductive layer beneath the ice. But then we saw it, or at least we saw what it might be leaving behind. The game-changing moment came from the Hubble Space Telescope, which on several occasions appeared to capture something astonishing: faint, fleeting plumes of water vapor erupting from Europa's south polar region, reaching hundreds of kilometers into space. It was as if the moon itself was giving us a glimpse of its life-giving secret, venting its ocean directly into the void. These weren't the continuous, predictable geysers of Enceladus. They were sporadic, elusive, and maddeningly difficult to confirm. Subsequent observations have sometimes seen them and sometimes not, creating a scientific debate as to their frequency and origin. The leading theory suggests that these plumes are erupting from fractures in the ice shell, driven by the same tidal forces that heat the moon's interior. As Jupiter's gravity squeezes and flexes Europa, it generates enough heat to keep a global ocean liquid. This internal energy might also create pockets of liquid water closer to the surface, or even cause the ice shell to partially melt, allowing water from the deep ocean to occasionally burst through like a cosmic pressure valve. The potential of these plumes is impossible to overstate. They offer a shortcut, a way to taste Europa's ocean without having to drill through kilometers of ice. A spacecraft flying through one of these eruptions could analyze its composition directly, searching for the complex organic molecules and salts that would be the telltale signs of a habitable environment or even of biological processes. This is the primary goal of one of the most anticipated missions in the history of planetary science, NASA Europa Clipper. Scheduled to launch in the coming years, this orbiter is a dedicated robotic detective designed to unlock Europa's secrets. It won't land. Instead, it will perform dozens of close flybys, mapping the ice shell in unprecedented detail, measuring its thickness with radar, and analyzing the moon's composition with a suite of powerful instruments. Most crucially, it will be equipped to fly through any plumes it encounters, using its mass spectrometers to literally sniff out the chemistry of the erupting material. It will be looking for the building blocks of life: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, as well as energy sources that could fuel metabolic reactions in the dark abyss below. The question of habitability on Europa hinges on a few critical factors that Clipper aims to investigate. First, is the ocean in contact with a rocky seafloor? If so, hydrothermal vents, like those that teem with life on Earth's ocean depths, could be providing the necessary chemical energy and nutrients to support entire ecosystems completely independent of sunlight. Second, what is the pH and salinity of the ocean? Is it a bitter, toxic brine or a more benign, watery environment? the plumes, if we can sample them, could hold the answers. The dream, of course, is to one day follow Clipper with a lander capable of melting or drilling through the ice. But for now, the prospect of analyzing the ocean from orbit is a revolutionary step forward. Europa represents the next great frontier in astrobiology, a world with potentially twice as much liquid water as all of Earth's oceans combined, hidden away in the darkness, waiting for us to discover if it is not just a watery world but a living one. But the quest for liquid doesn't end with the briny plumes of Europa or the fleeting streaks on Mars. As we journey to Saturn's largest moon, we find a world that feels both hauntingly familiar and utterly alien. A place with a hydrological cycle almost exactly like Earth's, but built from an entirely different set of ingredients. Titan is a world shrouded in a thick, orange haze, a moon larger than the planet Mercury, and it is the only other place in the solar system with a proven, active cycle of liquid flowing across its surface. But here, the rock is water ice, hard as granite in the -180 degrees Celsius cold, and the role of water is played by liquid methane and ethane. This is Titan's methane cycle, and it creates a landscape of breathtaking beauty and profound mystery. Imagine standing on a Titanian shoreline. The sky above is a perpetual, smoggy twilight, the sun a faint disk behind the orange haze. Before you stretches a vast, dark lake, not of water but of liquid hydrocarbons, its surface as still as glass. Rivers of methane have carved intricate deltas and channels into the icy bedrock, and in the distance, great dunes of organic sand, made from hydrocarbons that rained out of the atmosphere, stretch to the horizon. The Cassini spacecraft and its Huygens probe gave us this incredible portrait, revealing a world with weather, with evaporation, condensation, and precipitation. It rains liquid methane on Titan, filling its lakes and seas. It's a stunningly Earth-like process playing out with utterly alien chemistry. This is where we encounter the Moon's central enigma. Methane is not a stable molecule in Titan's upper atmosphere. The same sunlight that powers the cycle is also its destroyer. Ultraviolet radiation from the sun relentlessly breaks methane apart, converting it over time into more complex hydrocarbons like ethane and acetylene, and into the thick, orange smog of tholins that shrouds the moon. Based on the current rate of destruction, scientists have calculated that all the methane in Titan's atmosphere should have been completely broken down by solar radiation within a paltry 50 million years. That's a mere blink of an eye compared to the Moon's 4.5 billion-year age. The existence of a robust methane cycle today, with full lakes and flowing rivers, is therefore a physical impossibility unless there is a massive, hidden source constantly replenishing the lost gas. Titan is a system that is leaking, and we can see the leak, yet the lakes are full. Something must be actively filling them back up. This leaves planetary scientists with a captivating detective story. Where is Titan's methane coming from? Two primary theories have emerged, each painting a picture of a dynamic and complex world hidden beneath the icy surface. The first theory proposes a vast subsurface reservoir of liquid methane, a kind of global aquifer or hydrocarbon ocean trapped between layers of ice. This reservoir could act as a slow-release methane bank, gradually venting the gas into the atmosphere through cracks or porous regions in the icy crust to replace what is lost to photochemistry. This would neatly explain the replenishment, but it raises another question. How did such a massive reservoir form and remain isolated for billions of years? The second, and perhaps more thrilling, theory points to cryovolcanism, volcanoes that erupt with water ammonia slush instead of molten rock. In this scenario, Titan is not a dead world, but a geologically active one with a warm, liquid water ocean deep beneath its icy shell. This internal ocean, kept liquid by tidal heating from Saturn's gravity, could be rich in dissolved gases, including methane. Cryovolcanoes could then act as conduits, bringing this methane-rich slurry from the deep interior up to the surface where the methane is released as a gas into the atmosphere. There is some tantalizing evidence for this from Cassini's radar and infrared data, which identified several geological structures that look suspiciously like volcanic domes and flows, though the evidence remains controversial and not yet conclusive. The implications of this mystery are profound. If the methane is being supplied by cryovolcanoes, it means Titan has a complex, layered interior with a heat engine powerful enough to drive geologic activity, and that its subsurface water ocean might be in chemical communication with the surface. This would create a truly astonishing possibility: two separate, interacting liquid environments on one world, a surface solvent of methane and an interior solvent of water, each potentially capable of supporting its own unique prebiotic chemistry. Titan's methane cycle is more than just a curious weather pattern. It is the surface expression of a deep and hidden world, a clue that this distant moon is not a static fossil but a dynamic body with secrets still locked in its icy heart, waiting for a future mission to finally sail its strange, dark seas and uncover the truth. Yet, even as we explore the strange chemistries of distant moons, the story of our own closest companion holds a mystery of truly cosmic proportions, a violent birth that forged the moon and yet left behind a scientific paradox that challenges the very details of that creation. Look up at the moon on any clear night, and you are witnessing the aftermath of the single most violent event in Earth's history. The prevailing theory, the giant impact hypothesis, paints a breathtakingly dramatic picture. In the chaotic early solar system, about 4.5 billion years ago, a young, still molten Earth was sharing its orbit with a myriad of other planetary embryos. One of these, a Mars-sized world scientists have named Theia, found itself on a catastrophic collision course. This was not a simple sideswipe, it was a head-on, obliterating impact. Theia struck Earth with such unimaginable force that it is believed to have vaporized upon impact, melting and merging its iron core with our own planet's while simultaneously blasting a colossal torrent of molten rock and vaporized mantle from both worlds into orbit around Earth. In this searingly hot, glowing disk of debris known as a cynosure, the story goes that our moon began to coalesce. The material in this disk, a mixture of Theia's mantle and a significant portion of Earth's own, quickly clumped together under its own gravity, eventually forming the spherical body we know today. This theory elegantly explains so much about our lunar partner. It accounts for the moon's surprisingly large size relative to Earth, a ratio unique in the solar system. It explains why the moon has such a small iron core. Theia's core would have merged with Earth's, leaving the orbiting disk of debris primarily composed of lighter mantle material. It even explains the moon's orbital dynamics and its tidal locking. For decades, this has been the dominant, beautiful, and terrifying creation story for the Earth-Moon system. However, as with all good mysteries, a crucial piece of evidence emerged that didn't quite fit the narrative. When the Apollo astronauts brought back hundreds of pounds of lunar rocks, they provided scientists with the ultimate geological time capsule. For years, the rocks seemed to support the impact theory, but as our analytical tools became incredibly precise, allowing us to measure the isotopic signatures of elements like oxygen, titanium, tungsten, and silicon with astounding accuracy, a profound problem emerged. You see, isotopes are like elemental fingerprints. Every planetary body in the solar system has a slightly different mix of them, a unique signature inherited from its specific region of the primordial solar nebula. Theia, having formed in a different part of the solar system, should have had a noticeably different isotopic fingerprint from Earth. Therefore, if the moon is primarily made from Theia, its rocks should carry that foreign signature. But they don't. The isotopic compositions of lunar and terrestrial rocks are, for all intents and purposes, identical. This finding sent shockwaves through the planetary science community. It's as if the genetic code of the moon and Earth are twins, a result that the standard giant impact model simply cannot easily produce. If the Moon is made from another world, why does it look exactly like Earth? This isotopic crisis has forced scientists to reconsider and refine the original hypothesis, leading to a suite of fascinating new ideas. One compelling theory suggests that Theia and Earth might have been isotopic twins from the start, forming from material in the same orbital neighborhood and therefore having nearly identical compositions from the beginning. While possible, many consider this a somewhat convenient and statistically unlikely solution. Other models have dramatically altered the nature of the impact itself. Perhaps Theia was much larger than previously thought, delivering a hit so enormous that the resulting synestia was so thoroughly mixed and homogenized that the isotopic signatures of the two bodies were completely blended into one before the Moon condensed. Another radical idea is that the impact was far more violent and energetic, not just melting but completely vaporizing a huge portion of both worlds. In this extremely hot vapor cloud, the atoms of both bodies could have exchanged isotopes freely, erasing their distinct histories and emerging with a single, uniform signature. There's even a hypothesis involving a fast-spinning early Earth. If our planet was rotating much faster before the impact, a glancing blow from Theia could have ejected primarily Earth material, with Theia's remains being mostly absorbed into our planet's core. Each of these new models is a testament to scientific ingenuity, but each also comes with its own set of complications and trade-offs. A larger impactor or a more energetic collision might solve the isotope problem, but it could make it harder to explain other aspects of the Earth-Moon system, such as its angular momentum. The debate is far from settled, and it underscores a humbling truth. We may have witnessed the aftermath of our Moon's birth, but we are still deciphering the exact nature of the cataclysm that caused it. The mystery of the Moon's origin is a powerful reminder that even the most elegant and well-accepted theories in science must constantly be tested against new evidence, and that the greatest stories of our cosmic neighborhood are often written in the subtle atomic signatures locked inside a rock. This isotopic dead end has sent planetary scientists back to the drawing board, forcing them to reimagine the entire cataclysm with a new level of creative and violent detail. If the standard giant impact model is too neat, too clean to explain the geochemical twinship of the Earth and Moon, then perhaps the reality was far more extreme. One of the most captivating new ideas is the synestia model. Forget a simple impact between two solid spheres. Picture this instead. The colossal energy of the Theia impact was so unimaginably vast that it didn't just melt the two bodies, it completely vaporized a significant portion of both. The young Earth and its obliterated impactor would have been transformed into a searing, donut-shaped cloud of rock vapor, a swirling, super-hot structure known as a synestia with the dense, remaining core of Earth at its center. In this churning, homogenized maelstrom, the atoms of both worlds would have been thoroughly and completely mixed, like blending two colors of paint into a single, uniform hue. The Moon would then have begun to condense from the outer edges of this torus of vapor, forming from a cloud of material that already bore the perfectly blended isotopic signature of the combined Earth-Theia mixture. This model elegantly solves the isotopic crisis by ensuring the Moon forms from a well-stirred soup, but it requires an impact of such staggering violence that it pushes the boundaries of what we think is physically possible. A less extreme but equally fascinating alternative is the multiple impact hypothesis. This theory suggests our Moon wasn't born from one single definitive blow, but from a whole series of smaller, successive collisions with various planetary embryos during Earth's violent infancy. Each impact would have kicked up a disk of debris which would have coalesced into a small moonlet. Over time, a swarm of these moonlets would have eventually merged through a process of accretion, gradually building the single large moon we see today. The beauty of this model is that it doesn't rely on one statistically rare, perfectly sized impactor. Instead, it leverages the known chaos of the early solar system, where such impacts were commonplace. The isotopic similarity is explained by the fact that the Moon would be an amalgam of material from many different impactors that had already been accreted by the early Earth, all sharing a similar compositional heritage from our orbital neighborhood. While this avoids the need for a perfect isotopic twin in Theia, it introduces new dynamical challenges, such as getting all these moonlets to merge into one large body instead of forming a complex ring system or multiple moons that might eventually collide destructively. Yet another perspective challenges the very nature of the impactor. Some researchers propose that Theia was not a Mars-sized object, but something much larger, perhaps even a primordial planet that was still mostly molten and undifferentiated at the time of impact. Striking a partially formed Earth, this giant impactor could have merged its core seamlessly while ejecting a disk of material primarily from Earth's own mantle, neatly sidestepping the isotopic problem entirely. Other, more niche ideas have also been proposed, such as the fission theory, a very old concept that suggests the early, rapidly spinning Earth flung off a blob of its own mantle, which became the Moon. While this easily explains the isotopic match, it fails to account for the angular momentum of the Earth-Moon system and the Moon's oxygen-poor composition compared to Earth's mantle. The enduring power of this mystery lies in the fact that no single theory currently provides a perfect, elegant solution that satisfies every line of evidence: the dynamics, the geochemistry, the geology. Each model fixes one problem only to create another. The synestia model requires incredible energy, the multiple impact scenario has dynamical headaches, and the large impactor idea relies on a specific planetary state. This ongoing debate is a spectacular example of the scientific process in action. It shows how a single, inconvenient data point, the isotopic identity of lunar rocks, can overturn a beautiful and well-established story, forcing a burst of creative thinking and the development of ever more sophisticated computer simulations. The origin of our Moon is not a settled chapter in a textbook. It is a live, active, and thrilling field of research, a cosmic cold case where the clues are written in the atoms of ancient rocks and the orbital dance of two intertwined worlds. We are still piecing together the precise details of the violent birth that shaped our planet and gave us our constant celestial companion, a reminder that even the most familiar object in the night sky holds profound and unresolved secrets. Now we turn our gaze from the mysteries of distant worlds and moons to the very heart of our solar system, to the star that makes all life on Earth possible, and we find that it, too, holds a secret so counterintuitive it seems to defy the very laws of physics. If you were to stick a thermometer into the surface of the Sun, it would read a blistering 5,500 degrees Celsius. That's hot enough to vaporize any material we know. But if you then lifted that thermometer up into the Sun's outer atmosphere, a shimmering, pearly white halo visible during a total solar eclipse called the corona, the reading would skyrocket to an incomprehensible 1 to 2 million degrees Celsius. This is the solar corona heating problem, a paradox that has baffled solar physicists for decades. How can the Sun's atmosphere be hundreds of times hotter than its surface? It's as if you walked away from a fire and instead of getting colder, you suddenly found yourself immersed in flames that were exponentially hotter. This isn't just a minor anomaly, it's a fundamental violation of our basic understanding of thermodynamics, and solving it is key to understanding the very nature of our star. For a long time, this was a mystery we could only observe from afar. But now, for the first time in history, we have a spacecraft that is literally touching the Sun. NASA Parker Solar Probe is a mission of breathtaking audacity, designed to fly through the corona itself, repeatedly diving closer to the Sun than any human-made object has ever gone, all in an effort to finally solve this puzzle. The data it is sending back is already revolutionizing our understanding, and it points to three primary competing theories that might explain this cosmic heating phenomenon. The first and perhaps most dramatic candidate is a process known as magnetic reconnection. The Sun is a tangled ball of magnetic fields generated by the churning, electrically conductive plasma in its interior. These field lines are constantly being twisted, stretched, and knotted by the Sun's rotation. Sometimes these strained field lines snap, breaking and reconnecting in a new, lower-energy configuration. This reconnection event is like uncorking a colossal bottle of champagne, releasing a tremendous amount of stored magnetic energy in an explosive instant. This energy is dumped directly into the surrounding plasma, heating it to millions of degrees. If these reconnection events are happening on a small, constant scale all over the Sun, what scientists call nanoflares, they could provide the continuous energy input needed to heat the entire corona. Parker Solar Probe is hunting for the signatures of these tiny, ubiquitous explosions, and early data suggests it is finding them, providing strong support for this mechanism. The second major theory involves the transfer of energy by waves. The Sun's surface is constantly boiling with convection, a churning motion not unlike a pot of water coming to a boil. This convulsive motion generates powerful waves that travel outward through the solar atmosphere. Two types of waves are prime suspects. The first are acoustic waves, which are essentially sound waves carrying energy. The second, and more promising, are magnetic waves called Alfvén waves. Imagine flicking a rope that is tied to a post. A wave travels down the length of the rope. Now, imagine the rope is a magnetic field line rooted in the Sun's surface. Convective motions at the surface can flick these field lines, sending powerful Alfvén waves racing upward along them into the corona. As these waves travel into the thinner atmospheric layers, they grow in amplitude until they eventually break, like an ocean wave on a shore, dissipating all their pent-up energy as heat. It's a less violent process than magnetic reconnection, a constant, rhythmic heating like a drumbeat that steadily warms the atmosphere. Parker's instruments are tuned to detect the telltale signatures of these waves, and it has already observed Alfvén waves large enough to potentially contribute significant energy, though whether they carry enough power to account for the extreme temperatures remains an open question. A third, more recent idea combines elements of both theories. It suggests that the corona is heated by an incessant rain of tiny jetlets and picoflares. The Sun's surface is covered in a fine pattern of cell-like structures called granulation. At the boundaries of these cells, small-scale magnetic phenomena are constantly occurring. The theory proposes that countless tiny jets of plasma are being launched from these boundaries, and innumerable minuscule magnetic reconnection events are flaring all the time. Individually, each event is too small to account for much, but collectively, they could provide a constant carpet bombing of energy that superheats the entire corona. This would be like heating a room not with a single large bonfire, but with trillions of microscopic matches all being struck at once. The intense work to solve this mystery is about far more than just academic curiosity. The corona is the source of the solar wind, that constant stream of charged particles that flows outward from the Sun and bathes the entire solar system. The processes that heat the corona also accelerate this wind to tremendous speeds. Violent eruptions from the corona, like solar flares and coronal mass ejections, can unleash storms of radiation and charged particles that, when directed at Earth, can cripple satellites, disrupt power grids, and pose a radiation hazard to astronauts. Understanding how the corona works is the first step toward predicting this space weather, allowing us to better protect our technology-dependent civilization. The Parker Solar Probe, by flying directly into the furnace, is our greatest hope for untangling this knotted problem. Each daring dive through the corona brings back new data, helping us weigh the evidence for nanoflares against Alfvén waves and for jetlets against picoflares. The solution likely doesn't lie in one single theory, but in a complex combination of all these processes, a symphony of magnetic and plasma physics playing out on a scale we are only just beginning to perceive. The mystery of the Sun's hot corona is a stunning reminder that even our own star, the most familiar object in our sky, still operates by rules we have not yet fully deciphered. For centuries, humans have looked to the Sun as a symbol of constancy, an unwavering beacon in the sky. But as our scientific understanding has grown, we've learned that our star is anything but steady. It has a heartbeat, an 11-year cycle of activity where sunspots, flares, and eruptions ebb and flow. But even this rhythm can sometimes falter, and the most dramatic pause in this solar song occurred during a period we now call the Maunder Minimum. For roughly 70 years, from about 1645 to 1715, the Sun's face became remarkably blank, where astronomers of the time, like the aptly named Edward Maunder, expected to see the usual ebb and flow of dark sunspots. They observed almost nothing. This wasn't just a quiet season, it was a profound silence that coincided with some of the coldest winters ever recorded in the Northern Hemisphere, a climatic period often referred to as the Little Ice Age. The connection seems too compelling to ignore, a hibernating sun and a frozen Earth, but the true nature of that link and the deeper mystery of what causes these grand minima in the first place remains one of the most critical puzzles in solar physics, with direct implications for our future climate and technological society. The sheer scale of the Maunder Minimum's effect is what makes it so captivating. Imagine a time when the River Thames in London regularly froze over so solidly that they could hold winter festivals, complete with ice skating and market stalls right on the river. This was the reality during the late 17th century. Paintings from the era show a world in a deep freeze, and historical records from Europe and North America describe unusually long, brutal winters and abbreviated, cool summers that led to failed harvests and widespread famine. The coincidence in timing with the near-total absence of sunspots strongly suggests a correlation. The leading theory is that during a solar minimum, the Sun's total irradiance, the amount of energy it emits, decreases slightly. While this change is minuscule, typically less than 0.1%, our climate system is exquisitely sensitive to such small, persistent forcings. A slightly dimmer sun over decades can nudge global atmospheric circulation patterns, potentially leading to regional cooling, particularly in the Northern Hemisphere. It's a powerful reminder that we are, in every sense, creatures of our star, intimately tied to its every mood swing. However, the story is far from simple. The Little Ice Age actually began before the Maunder Minimum, and its causes are now understood to be a complex cocktail of factors. Increased volcanic activity during this period pumped vast quantities of sunlight reflecting aerosols into the stratosphere, which would have had a significant cooling effect. Some climatologists also point to changes in ocean circulation patterns. So, while the quiet sun almost certainly played a role, it was likely the final straw that broke the climate's back, a contributing factor that amplified an already cooling trend rather than the sole cause. This complexity is what makes studying grand minima so crucial today. If we can understand the sun's true influence on past climate, we can far more accurately predict its role in our current era of human-driven global warming. It helps us separate the solar signal from the much louder noise of greenhouse gas emissions. This leads us to the central, burning mystery: what actually causes the sun to enter these extended periods of quiet? The 11-year solar cycle is driven by a process called the solar dynamo, a complex interplay between the sun's rotation, its convection zone where hot plasma rises and falls, and the magnetic fields this motion generates. Think of it as a gigantic, spinning electromagnetic engine deep within the sun. A grand minimum like the Maunder event is thought to represent a glitch in this engine, a period where the dynamo weakens considerably. But what triggers the glitch? One compelling theory involves the behavior of two key plasma flows inside the sun. The first is a fast-moving stream of plasma called the torsional oscillation, which acts like a conveyor belt, sweeping magnetic fields toward the poles. The second is the meridional flow, a slower, wider current that moves from the equator toward the poles near the surface and then dives back inward. Some models suggest that during the lead up to a grand minimum, these flows may change their speed or pattern, effectively short-circuiting the process that normally amplifies the magnetic field to create sunspots. It's as if the sun's internal transportation system for magnetic energy gets clogged or rerouted, preventing the usual buildup of activity. Another fascinating idea connects these minima to the gravitational influence of the planets. The sun doesn't sit motionless at the center of the solar system. It makes a small orbit around the solar system's barycenter, the common center of mass, which is constantly shifting due to the pull of the giant planets, particularly Jupiter and Saturn. This motion can inject a rhythmic torque into the sun's outer layers. Some scientists have found a correlation between the timing of grand minima and specific alignments of the planets, proposing that this gravitational pumping can influence the sun's internal dynamics, perhaps helping to trigger or sustain a period of dormancy. While this remains a controversial and unproven hypothesis, it's a stunning concept that the silent, clockwork motion of the planets could potentially nudge the star they orbit into a different state of being. Unraveling this mystery is not merely an academic exercise, it is a matter of practical urgency for our modern world. A future grand minimum would have a double-edged sword effect on our planet. On one edge, the slight reduction in solar irradiance might impose a very small, temporary cooling effect on Earth's climate, a minuscule counterweight to the overwhelming warming from greenhouse gases. But the other edge is far sharper and more dangerous for our technology-dependent civilization. A quiet sun does not mean a safe sun. In fact, it's during the transition periods into and out of these minima that the sun can become unpredictably violent. Furthermore, a dormant sun's magnetic field weakens and shrinks. This weakened magnetic shield allows more galactic cosmic rays, high-energy particles from deep space, to penetrate into the inner solar system. This poses a greater radiation risk to astronauts and can even affect air travel by increasing radiation exposure at high altitudes. For a society built on satellites, power grids, and GPS, understanding and predicting the sun's long-term cycles is a critical part of safeguarding our infrastructure. The Maunder minimum is not just a historical curiosity, it is a precedent, a warning from the past of our star's capacity for profound change, and a testament to the intricate and often fragile connection between a spinning ball of plasma in the void and the world we call home. Yet, even as we grapple with the sun's grand cycles, another mystery emerged not from the fiery heart of our star, but from the icy, silent depths of interstellar space, a puzzle so subtle it was discovered not in a flash of light, but in the agonizingly slow drift of a few bits of data. In the 1970s and 80s, humanity's first ambassadors to the outer solar system, the Pioneer 10 and 11 spacecraft, were on their way to becoming the first human-made objects to ever leave our planetary neighborhood. As they cruised silently toward the stars, teams back on Earth were tracking their positions with exquisite precision, using the Doppler shift of their radio signals to measure their velocity down to a fraction of a millimeter per second. And that's when they found it, an anomaly. Both spacecraft, despite having expended all their fuel and being under the sole influence of gravity, were experiencing a tiny, unexplained deceleration. It was as if a faint, invisible hand was reaching out from the direction of the sun, ever so gently applying the brakes. This minuscule tug, just 10 billion times weaker than the gravity we feel on Earth's surface, became one of the most tantalizing puzzles in modern physics, the Pioneer Anomaly. For nearly 2 decades, this persistent drift was a thorn in the side of physicists and a spark for the imaginations of theorists. The most thrilling possibility was that we had stumbled upon evidence of new physics, a crack in the foundation of Einstein's theory of general relativity. Perhaps the laws of gravity behaved differently over vast distances. Maybe dark matter was exerting a drag we hadn't anticipated. Some even proposed exotic ideas like the existence of higher dimensions subtly altering the force of gravity in our own. The Pioneer Anomaly became a beacon for those who believed our understanding of the cosmos was incomplete, a tiny data point that promised a revolutionary rewrite of the textbooks. But science has a remarkable way of solving its own mysteries, often through a combination of relentless detective work and technological advancement. The key to unraveling this enigma wasn't found by looking outward for new physics, but by looking inward at the probes themselves. The leading theory began to focus on a remarkably mundane source: heat. The Pioneer probes were powered by radioisotope thermoelectric generators, or RTG. These devices create electricity from the natural decay of plutonium, a process that generates a significant amount of waste heat. The spacecraft were designed to radiate this heat away into space to prevent overheating. Crucially, this heat wasn't being emitted symmetrically. More of it was being radiated from the aft end of the craft, the side facing away from the sun where the RTGs were mounted, than from the front. This created a tiny but very real photon thrust. Every photon of heat radiating from the spacecraft carries with it a minuscule amount of momentum. If this radiation is not perfectly balanced, the net effect is a tiny force pushing in the opposite direction. In the case of the Pioneers, the slightly greater radiation from the back of the probe was effectively creating a very weak photon rocket that was pushing back against the direction of travel, perfectly mimicking an anomalous deceleration toward the sun. When researchers undertook the Herculean task of reconstructing the entire thermal design and power history of the decades-old spacecraft, creating complex computer models of how heat flowed across every bolt and panel, they found that this thermal recoil force could account for the vast majority of the mysterious deceleration. Yet, in a twist befitting this journey of cosmic puzzles, the story doesn't end with a perfectly neat solution. Even after the most sophisticated thermal models accounted for every watt of power and every radiant surface, a tiny sliver of the anomaly remained unexplained, a residual acceleration so small it lingers at the very edge of detectability. This leftover signal is now so faint that it could be an artifact, an accumulation of unmodeled tiny errors in our understanding of the spacecraft's complex design or the subtle pressure of the solar wind. Or it could be the ghost of that original thrilling possibility, a whisper of something truly new still hiding in the data. The legacy of the Pioneer Anomaly is a beautiful lesson in scientific humility. It reminds us that the line between a systematic error and a fundamental discovery is often razor-thin, and that the most exciting signals sometimes lead us not to new universes, but to a deeper understanding of the ingenious machines we build to explore them. Yet while the Pioneer Anomaly was a slow, subtle drift in data, our next mystery arrived not as a whisper, but as a thunderclap, a burst of signal so powerful and so perfect that the astronomer who discovered it was moved to scrawl a single, stunned word on the printout: "Wow." It was the evening of August 15, 1977, at Ohio State University's Big Ear radio telescope. This massive instrument was methodically scanning the sky, listening to the cosmic radio static on a frequency near 1420 MHz, a special band known as the hydrogen line. It's a quiet channel largely protected from human interference, and it's a frequency that many scientists had theorized would be a logical choice for any civilization trying to announce its presence across the interstellar void. For the most part, the telescope's chart recorder dutifully printed out a steady, unremarkable squiggle representing the background noise of the universe. But then, at exactly 10:16 p.m., the pen jumped. It didn't just twitch, it surged dramatically off the chart, peaking at a signal strength 30 times louder than the ambient cosmic noise. It held this incredible intensity for a full 72 seconds, the exact amount of time it took for the Big Ear's fixed focus to sweep that particular point in the sky, before it vanished as suddenly and cleanly as it had appeared. The signal itself was a textbook example of what scientists working with the search for extraterrestrial intelligence, or SETI, had been hoping to find. It was a narrowband signal, meaning it was concentrated on one very specific frequency, much like a radio station here on Earth. Natural cosmic objects like pulsars or quasars typically broadcast their radio whispers across a wide range of frequencies, a broad static hiss. The WOW signal's narrow focus was the first hallmark of a potential artificial, engineered transmission. Secondly, it exhibited a clear rise and fall in intensity, exactly matching what you would expect as the telescope's beam swept across a fixed-point source in the heavens. This wasn't some burst of localized interference. Its behavior was precisely consistent with an origin far out in space. The astronomer on duty that night, Jerry Amon, meticulously circled the alphanumeric code on the printout 6-5 that represented the signal's unprecedented strength, and in a moment of pure, astonished exhilaration wrote, "Wow." In the margin, that single word named one of the most enduring and tantalizing mysteries in the history of astronomy. In the decades since, the search for an explanation has become a scientific detective story of the highest order, a relentless effort to find a prosaic cause for something that feels anything but ordinary. The immediate suspect, as always, was human-made interference. Could it have been a secret military transmission, a reflection from a piece of space debris, or a satellite? The problem is that the frequency of the WOW signal, the 1420 MHz band, is internationally protected. It's reserved exclusively for radio astronomy, specifically for listening to the natural emission of hydrogen atoms in space. No earthly transmitters are legally allowed to broadcast on it, making terrestrial interference highly unlikely, though not completely impossible. Furthermore, the Big Ear telescope had a unique design with two feed horns, each scanning slightly different parts of the sky a few minutes apart. A signal originating from Earth or its immediate vicinity would have appeared in both horns. The WOW signal was detected by only one. This crucial detail strongly argues against a local source and points firmly to an origin in deep space. This realization launched a multi-decade quest to find it again. If it was a beacon from another civilization, why would it transmit for just 72 seconds and then go silent forever? Perhaps it was a targeted message, briefly aimed our way before the sender moved on to scan another star. Maybe it was a powerful but accidental burst of radiation from an advanced civilization's technology. The most obvious test was simply to look again. Astronomers have pointed powerful radio telescopes, including the Very Large Array, back toward that same precise patch of sky in the constellation Sagittarius over 100 times since then. They have scanned that frequency and millions of others around it. The result has been a profound and utter silence, not a single blip, not a hint of a repeat performance. This failure to redetect the signal is in itself a major clue. It has led many scientists to argue for a natural, albeit extremely rare, explanation. One compelling theory involves comets. In 2016, an astronomer proposed that two previously unknown comets, called 266P/Christensen and 335P/Gibbs, happened to be transiting through that exact region of sky in the summer of 1977. These comets are surrounded by massive clouds of hydrogen gas, which could theoretically emit a strong, narrowband signal right at the magic frequency of 1420 MHz. The idea is elegant, explaining both the signal's specificity and its one-off nature. However, this hypothesis has been heavily criticized. Other astronomers have pointed out that the comet's known hydrogen clouds are far too diffuse to generate a signal anywhere near that powerful, and that the frequency of emission from hydrogen in space is never quite as narrow and clean as the WOW signal was. The comet theory, while creative, is generally considered an unlikely solution. Other natural explanations point to bizarre astrophysical events that we might only witness once. Perhaps it was an incredibly intense and focused burst of cosmic maser activity, a natural laser-like amplification of radio waves occurring in a distant interstellar gas cloud under just the right conditions. Maybe it was a previously unobserved phenomenon related to a microlensing event, where the gravity of a passing star or planet briefly focused and amplified a much weaker background signal from a distant quasar, creating a fleeting, brilliant flash in radio waves that we were lucky enough to catch. These are all possibilities, but they require a chain of highly specific and improbable coincidences. And so, nearly 50 years later, the WOW signal remains in a category all its own. It is the only signal in history that so perfectly matched the expected signature of an artificial interstellar transmission that it cannot be easily dismissed, yet it remains stubbornly isolated and unexplained. It is the ghost in the machine of SETI, a constant reminder of both the immense promise and the immense challenge of listening for others in the cosmic ocean. It represents the ultimate what if, a 72-second gust of wind that felt for all the world like a voice calling out, only to be swallowed again by the eternal silence. It is a mystery that fuels our imagination and our science in equal measure, a single, enigmatic data point that continues to ask the biggest question of all: were we, for one brief moment in 1977, not alone? Between the orbits of Mars and Jupiter lies a sprawling, cosmic construction site frozen in time, the asteroid belt. A popular image, often reinforced by science fiction, depicts this region as a chaotic and impossibly dense debris field where spacecraft must dodge and weave through a perpetual meteor storm. The reality is far different, and in that difference lies a profound mystery. If you were to stand on any asteroid, your naked eye would likely see nothing but the empty blackness of space. The nearest neighboring asteroid would be millions of kilometers away. This is not a packed junkyard, but a vast and mostly empty expanse, which leads to a fundamental question. Why is this material here at all? Why didn't it follow the same rule as the rest of the inner solar system and coalesce into a proper planet? The answer seems, at first glance, beautifully simple: Jupiter. The gravitational might of the solar system's largest planet is the obvious culprit, a colossal bully whose presence prevented a world from ever forming. But as we look closer, the story becomes wonderfully complex, a tale of migration, violent collisions, and a diversity of objects that tells a much richer history than a simple gravitational prohibition. The classic explanation is one of gravitational resonance. As the first and largest planet to form, Jupiter's immense gravity dominated the early solar system. The region where the asteroid belt now resides sits perilously close to this giant. The idea is that Jupiter's gravity created powerful orbital resonances, specific zones where the orbital period of a potential planetesimal would be a simple fraction of Jupiter's own. An object in a 2-to-1 resonance, for example, would orbit the Sun twice for every one of Jupiter's orbits, passing that same point in its orbit again and again. It would feel a periodic gravitational tug from the giant planet. These repeated, rhythmic tugs would have acted like a parent pushing a child on a swing, adding energy to the object's orbit over time. Instead of gently coalescing with other material, these planetesimals would have had their orbits dramatically altered, ejected from the solar system entirely, or sent on a collision course with the inner planets. This process would have efficiently stripped the region of most of its mass, preventing any single large body from accumulating and leaving behind only the sparse collection of objects we see today. It's a clean, elegant, and powerful theory. However, the asteroids themselves tell a more complicated story through their sheer variety. We once thought the belt was a relatively uniform collection of rocky leftovers, but modern observations reveal it to be a meticulously sorted museum of solar system history. The belt is not a random mix, it is sharply divided by composition. Moving outward from the Sun, we first encounter the S-type or silicaceous asteroids. These are rocky, metallic bodies, rich in silicon and oxygen, and they dominate the inner portion of the belt. Further out, we find the C-type or carbonaceous asteroids. These are darker, primitive bodies loaded with carbon, water ice, and organic compounds, and they make up the majority of the belt's population. This clear separation is a massive clue. It suggests that the material in the belt did not form in a single, placid ring around the Sun. Instead, it points to a dramatic and dynamic process of mixing and sorting that occurred after the initial formation of the planets. This is where the Grand Tack hypothesis enters the picture, one of the most fascinating and revolutionary ideas in modern planetary science. It proposes that the young Jupiter did not simply sit in its orbit and prevent a planet from forming. It went on a monumental journey. According to this model, Jupiter began forming much closer to the Sun, at a distance of perhaps only 3.5 astronomical units, well within the current orbit of the asteroid belt. As it grew, it began to migrate inward toward the Sun, plowing through the primordial disk of gas and dust. This inward march would have scattered the material that was there, sending a wave of debris flying. But then, according to the model, Saturn formed. As Saturn grew, its own gravitational influence began to pull on Jupiter. The two giants became locked in a special orbital configuration called a mean motion resonance, and this gravitational partnership reversed Jupiter's migration. Like a sailboat tacking against the wind, Jupiter changed course and migrated back outward to its current position. This round trip, this grand tack, would have utterly ravaged the asteroid belt region twice over. It would have scattered the original population of asteroids, and then, on its outward journey, Jupiter would have dragged with it a new population of icy, carbon-rich planetesimals from the far outer solar system, depositing them in the outer belt. This incredible migration story explains the compositional divide perfectly. The original, warmer inner belt material became the S-types, while the imported, cold outer solar system material became the C-types. Yet the violence did not end there. The belt also bears the scars of epic, planet-shattering collisions. We see families of asteroids, groups of objects that share nearly identical orbits and compositions. These are the fragments of much larger parent bodies that were utterly demolished in catastrophic impacts. The most stunning example of this is the dwarf planet Ceres, the belt's largest resident. Ceres is not a simple rock. Evidence suggests it is a differentiated world with a rocky core and an icy mantle, and it may even possess a subsurface ocean. It is a protoplanet, a world that almost was, whose growth was likely stunted first by Jupiter's migration and then by the chaotic environment it created. Other large asteroids like Vesta show similar evidence of a complex history, with a surface marked by a colossal impact basin from an event that nearly tore it apart. The asteroid belt is not merely a collection of building blocks that never assembled. It is a graveyard of failed planets and a monument to the violent, chaotic processes that built the solar system we see today. It is a place where the competing influences of a migrating giant and relentless collisions created a stable, if sparse, equilibrium, a permanent reminder of how different our cosmic neighborhood might look if just a few gravitational details had played out another way. While the asteroid belt offers a fossil record of our solar system's violent infancy, some of its most pristine and unaltered relics occasionally break free, journeying inward toward the Sun to put on one of nature's most spectacular shows. For millennia, comets have been seen as harbingers, their sudden appearance in the night sky both awe-inspiring and terrifying. With their brilliant heads and long, flowing tails, they seem like cosmic visitors with a singular purpose. But as we've studied them more closely, we've found that these beautiful displays are actually the signature of profound and complex physics, some of which continues to defy our expectations. The most visually perplexing behavior is the way a comet can seemingly grow not one, but two completely separate tails that point in wildly different directions. It's a celestial magic trick that has a perfectly logical explanation, yet it reveals just how dynamic and intricate these icy wanderers truly are. The secret lies in understanding that a comet's tail is not something that streams out behind it like smoke from a rocket. Instead, it is something that is always being pushed away from the sun. The moment a comet's orbit brings it close enough to the sun, its frozen ice's water, carbon dioxide, methane, and ammonia begin to heat up and sublimate, turning directly from a solid into a gas. This process releases huge amounts of dust and rock that were trapped within the ice, creating a vast, glowing cloud around the nucleus called the coma. Now, two separate forces from the sun go to work on this material. The first is the solar wind, a constant supersonic stream of charged particles, protons and electrons flowing outward from the sun. This wind electrically charges or ionizes some of the gases in the coma, creating a plasma. Because these ions are electrically charged, they are fiercely loyal to the magnetic field carried by the solar wind itself. This forces the ion tail to always point directly away from the sun in a perfectly straight line, like a weather vane in a hurricane. The second force is sunlight itself, or more precisely, the radiation pressure from the sun's photons. This gentle but constant push affects the much larger dust particles released from the comet. The dust tail also points away from the sun, but it follows a different rule. Because the dust particles are heavier and are influenced by the comet's own orbital motion, they don't get swept into a straight line. Instead, they form a broader, brighter, and often gently curved tail that traces the comet's orbital path. So, as a comet rounds the sun and begins to head back out into the solar system, a fascinating visual reversal occurs. The straight ion tail now leads the way, pointing directly away from the sun ahead of the comet, while the curved dust tail follows behind. This creates the illusion that the comet is traveling tail first, which in a way it is. This dual tail phenomenon is a beautiful demonstration of physics in action, a real-time experiment showing the difference between the influence of magnetic forces on plasma and the gentle nudge of light on dust. But the true revolution in our understanding came not from watching comets from afar, but from visiting one directly. The European Space Agency's Rosetta mission was a masterpiece of precision and daring, designed to do what had never been done before, not just fly by a comet, but orbit it and land a probe on its surface. For over 2 years, the Rosetta spacecraft danced around comet 67P/Churyumov-Gerasimenko, mapping its bizarre rubber duck shape and studying its every belch and shudder as it swung around the sun. The Philalander's bumpy, unpredictable touchdown was a nerve-wracking moment, but its brief periods of operation, combined with Rosetta's orbital data, delivered a treasure trove of discoveries that completely upended the textbook image of a comet as a simple, dirty snowball. The most stunning find was in the comet's chemical composition. Rosetta's mass spectrometers sniffed the coma and found a veritable soup of complex organic molecules, the building blocks of life as we know it. They detected glycine, a fundamental amino acid, alongside phosphorus, a key component of DNA and cell membranes. They found alcohol and sugar molecules. This was profound evidence that the raw ingredients for life are not unique to Earth. They are being forged in the frigid depths of space and can be delivered throughout the solar system by these icy couriers. This supports the captivating theory that comets may have played a crucial role in seeding the early Earth with the water and organic compounds necessary for life to eventually emerge. However, these discoveries also created a new and deeper mystery about the comet's very origin. The water vapor boiling off comet 67P had a specific isotopic fingerprint, specifically the ratio of heavy water which contains deuterium to regular water. This ratio is a powerful tracer of where in the early solar system an object formed. To everyone's surprise, the water on 67P was significantly different from the water in Earth's oceans. It had a much higher proportion of heavy water. This was a major blow to the long-held idea that comets were the primary source of Earth's water. It suggests that while comets certainly delivered some water and organics, the main delivery service for our oceans was more likely asteroids, which we know have a water fingerprint that matches our own. This forces a dramatic rethink of our solar system's early dynamics, implying that the Kuiper belt, where comets like 67P are thought to originate, is a far more chemically diverse place than we imagined, or that this comet formed in a different, more distant region entirely before being scattered inward. Furthermore, Rosetta revealed a surface and internal structure that was nothing like the soft, fluffy pile of ice and dust scientists had predicted. Instead, the comet was incredibly porous with a density less than that of ice, and its surface was remarkably hard and rigid, covered in a dark, crusty, organic-rich material. The comet's activity wasn't a gentle, uniform melting. It was a violent jetting process with powerful geysers of gas and dust erupting from specific, localized fractures in the crust. This suggests the comet's interior might be a pristine, unaltered relic, while its surface has been baked and altered by billions of years of cosmic radiation, creating a crispy outer shell that hides a volatile interior. The mission answered countless questions, but it left us with a more profound puzzle. If comets like 67P didn't supply our water, then what was their specific role in the construction of our solar system? Their complex chemistry proves they are more than simple ice balls. They are time capsules holding the recipe for the ingredients of life, but we are still learning to read the handwriting in which that recipe is written. Now, let's rewind the cosmic clock to the very dawn of the solar system, to a period of almost unimaginable violence that may have shaped the destiny of every rocky world, including our own. The story begins with the Apollo missions. When astronauts brought back the first samples of the Moon, scientists were eager to date the great, dark basins that form the iconic Man in the Moon. These massive impact scars, they assumed, would be ancient, dating back to the final chaotic stages of the Moon's formation over 4.5 billion years ago. But when they analyzed the rocks, the results were shocking. The crystals told a different story. The ages of these impact melts clustered not around 4.5 billion years, but around 3.9 billion years ago. This suggested that the Moon, and by extension Earth, Mercury, Venus, and Mars, had endured a terrifying and intense barrage of impacts hundreds of millions of years after the planets themselves had formed. This cataclysmic event was dubbed the Late Heavy Bombardment, and its existence has become one of the most heated debates in planetary science. If it happened, the Late Heavy Bombardment would have been an epoch of pure hell for the inner solar system. Picture the sky filled with fire, not with occasional shooting stars, but with a continuous rain of city-sized and even continent-sized asteroids, each impact releasing more energy than all of our planet's nuclear arsenals combined. The Earth's surface would have been a constantly churning cauldron of molten rock. Its nascent oceans flash boiled into steam over and over again, its earliest crust continually recycled back into the mantle. For any life that might have tentatively begun in quieter times, this would have been an existential threat, a sterilizing reset button pressed repeatedly across millions of years. Yet, paradoxically, it might also have been a catalyst. These impacts could have delivered vast quantities of water and the very organic building blocks of life, while the hydrothermal systems created in the aftermath of each colossal crash could have provided the perfect sheltered environments for the chemistry of life to begin anew. So what could have caused such a delayed apocalypse? The leading and most dramatic theory is the Nice model, named after the city in France where it was developed. This computer simulation suggests that the giant planets Jupiter, Saturn, Uranus, and Neptune did not form in their current positions. Initially, they orbited much closer together in a more compact, tranquil configuration. But gravity is a restless architect. Over hundreds of millions of years, the planets subtly influenced each other's orbits until Jupiter and Saturn fell into a special gravitational resonance. Saturn would complete exactly 2 orbits for every one of Jupiter's. This rhythmic tug was like a gravitational hammer blow to the entire solar system. It destabilized the orbits of Uranus and Neptune, sending them scattering outward like cosmic billiard balls. In their chaotic migration, they plowed through the vast disk of icy planetesimals left over from the solar system's formation, scattering them in all directions. A torrent of these frozen missiles was flung inward, bombarding the terrestrial planets and peppering the Moon with the craters we see today. In this scenario, the late heavy bombardment was not the tail end of planet formation, but a separate, distinct cataclysm triggered by the gravitational reshuffling of the solar system's giant worlds. However, a growing number of scientists argue that this elegant story is built on a foundation of sand, or rather, a foundation of moon rocks. The skeptical view, often called the lunar cataclysm null hypothesis, questions the very evidence for a spike in impact. The main issue is one of sampling bias. All of the Apollo landing sites are located on the near side of the Moon, and most of them are within or near the giant Imbrium Basin, one of the youngest and largest impact structures. The concern is that the Apollo samples didn't capture a global event, but merely dated one single, large basin-forming impact and its immediate aftermath. The material ejected by the Imbrium impact would have rained down across the entire near side, resetting the clock on countless smaller craters and creating the illusion of a sudden, planet-wide barrage, when in reality it might have just been one particularly bad day in a long period of declining impact rates. It's like finding a cluster of wrecked cars from a single massive pileup on a highway and concluding that every car in the world crashed on that same day. This critical reassessment forces a profound question. Was the late heavy bombardment a real solar system-wide event, or is it a ghost in the data, a story we've woven from a limited set of clues from one world? The debate is far from settled. Evidence from asteroids like Vesta, whose surface also shows signs of ancient resurfacing, provides some support for a broader event. Yet, the fact that we have no terrestrial rocks from this era, our planet's active geology, has erased the evidence means we may never have a definitive answer. The late heavy bombardment stands as a stark reminder of the challenges of reading a history book where most of the pages have been torn out, a tantalizing chapter in our solar system story that hangs in a delicate balance between a catastrophic truth and a compelling scientific myth. And so we arrive at the final mystery on our list, one that brings our journey full circle, from the farthest reaches of the Kuiper belt right back to the very heart of our solar system and the fundamental building blocks of the cosmos itself. It's a puzzle written not in the craters of a distant moon or the atmosphere of a gas giant, but in the faint spectral lines of the sun and stars, a deficit of a single, specific element that challenges our understanding of everything from stellar furnaces to the birth of the universe. This is the mystery of the missing lithium. To understand why this is so baffling, we need to rewind the clock to the absolute beginning. In the first few minutes after the Big Bang, the universe was a seething, unimaginably hot cauldron of fundamental particles. As it expanded and cooled at a ferocious rate, the conditions were just right for a brief, explosive period of nuclear fusion known as Big Bang nucleosynthesis. During this fleeting window, the first simple atomic nuclei were forged, vast amounts of hydrogen, a good portion of helium, and trace quantities of 2 other light elements, deuterium and lithium. This primordial recipe is a cornerstone of modern cosmology. We can calculate with incredible precision how much of each element should have been created, and for the most part, our observations of the oldest, most pristine regions of the universe match these predictions almost perfectly. The amounts of primordial hydrogen and helium we see align beautifully with the models, but when it comes to lithium, the numbers are stubbornly, undeniably wrong. The oldest stars in our galaxy, which formed from that pure, uncontaminated early material, contain only about 1/3 of the lithium that our theories of the Big Bang say they should. A huge portion of the universe's original lithium has simply vanished. This leaves cosmologists and astronomers with a profound question. Is the problem with our telescopes, or is it with our textbooks? There are two captivating and opposing possibilities. The first is that our understanding of the physics of the Big Bang is incomplete. Perhaps there is a subtle error in our models of those first frantic minutes. Maybe an unknown particle, like a certain type of neutrino, was present and interacted with the nuclear reactions in a way that suppressed lithium production. Or perhaps there is a gap in our knowledge of nuclear physics itself, a reaction rate or a resonance that we have miscalculated, throwing off the entire delicate balance of those primordial reactions. This would be a revolutionary finding, forcing us to rewrite the first chapter of the universe's history. The second, and perhaps more likely, explanation is that the Big Bang produced the correct amount of lithium, but something has been systematically destroying it ever since. The prime suspects in this cosmic theft are the stars themselves. Our Sun, for instance, has about 140 times less lithium in its surface layers than the material it formed from. We know that processes inside stars can burn and destroy lithium. The problem is that the standard models of stellar physics can't account for this much destruction. Lithium is a fragile element. It burns at a relatively low temperature of around 2.5 million degrees Celsius. In a star like our Sun, the surface layers are too cool to touch it, while the deeper interior is far too hot, meaning lithium should be safe in a narrow, intermediate layer. Our current models suggest that simple diffusion and mixing shouldn't be efficient enough to drag surface lithium down to its destructive doom in the core in the quantities we observe. This has forced astronomers to search for new and more efficient ways that stars might be shredding this element. One compelling theory involves rotation and magnetic fields. Young stars spin rapidly and have incredibly powerful magnetic activity. This can drive turbulence and create large-scale circulation patterns in their outer layers. Think of a colossal conveyor belt that dips deep into the star. This process, known as rotational mixing, could be constantly dragging surface material, including lithium, down into the hotter regions where it is obliterated. Another fascinating idea points to planet formation. As a young star is forming, the infalling material from the protoplanetary disk could somehow disrupt the star's outer layers, triggering deep mixing that burns off lithium before the star even settles into its main sequence life. The quest to solve this mystery is a perfect example of the scientific method at its best, connecting the unimaginably large scale of cosmology with the intricate details of stellar physics. Astronomers are hunting for lithium in every possible context, in the oldest stars in the Milky Way's halo, in binary star systems where one star has planets and the other doesn't, and in young star clusters where age and rotation rates can be compared. Each new observation is a piece of the puzzle. The solution will not only tell us what happened to the lithium, but will also provide a crucial key to understanding the inner workings of stars, the process of planet formation, and perhaps even the very first moments of creation. It's a humble reminder that sometimes the biggest secrets of the universe are hidden not in the dramatic collapse of a star or the flash of a supernova, but in the subtle, silent absence of a few atoms that were supposed to be there. And so, after this grand tour of 30 cosmic conundrums, what are we left with? Not a simple set of answers, but something far more valuable, a profound sense of wonder and a clear vision of just how much we have yet to learn. Our solar system, once imagined as a static and well-ordered clockwork of planets, reveals itself instead as a dynamic, chaotic, and breathtakingly enigmatic neighborhood. It is a place where small worlds shrink, where giant storms rage for centuries, where hidden oceans slosh in the darkness, and where the very origins of our own planet and moon are still hotly debated. Each mystery we've explored, from the phosphine in Venus's clouds to the silent, geometric perfection of Saturn's hexagon, is not a dead end for science. It is a beacon. These puzzles are the very engines of discovery, the unanswered questions that propel us to build better telescopes, design more daring spacecraft, and peer ever deeper into the cosmos with renewed curiosity. Think about the missions already on the drawing board, inspired directly by these enigmas. The quest to solve the methane mystery on Mars is a driving force behind the sample return campaign. The tantalizing possibility of life in the plumes of Europa is the reason the Europa Clipper mission will soon begin its journey. The bizarre chemistry of Titan's atmosphere is why we're designing drones to sail its hydrocarbon seas. Every single one of these 30 mysteries represents a future voyage, a puzzle waiting for its dedicated robotic detective. They remind us that exploration is not a chapter in a history book. It is a continuous, living process, a conversation between our curiosity and the universe's endless capacity to surprise us. This journey doesn't belong just to scientists in lab coats. It belongs to anyone who has ever looked up at the night sky and felt a sense of awe. That curiosity is the most powerful tool we have. So now we want to hear from you. Which of these 30 mysteries captured your imagination the most? Does the thought of a hidden planet 9 lurking in the dark fire up your sense of adventure? Are you captivated by the idea of diamond rain on Neptune, or does the sheer, ancient violence of our moon's birth story leave you stunned? Share your thoughts in the comments below. Let's have a conversation about the wonders in our own backyard. Our tour of the solar system's greatest unsolved mysteries may be complete, but the real story is just beginning. For every question we answer, a dozen new ones emerge from the data, each more fascinating than the last. This is the beautiful, unending process of science. It's a reminder that the universe is not a puzzle to be solved, but a mystery to be embraced. So keep looking up, stay curious, and never stop wondering about the incredible, strange, and magnificent cosmos we call home.